In a dark room, two clocks are ticking. They are not in the same room. They are not even in the same century. One of them began counting 13.8 billion years ago. In the moment the universe first became transparent to light, it is embedded in the oldest glow we can see, a faint wash of microwaves that arrives from every direction we point a telescope. The other clock is running now, in the pulses of stars that live and die in galaxies we can name. It counts distance by the light of exploding suns. Both clocks are measuring the same thing: how fast the universe is growing, how quickly the space between things is stretching. They give different answers. The James Webb Space Telescope was built, in part, to find out why. It is the most powerful telescope ever launched, a mirror 6.5 meters across, folded into a rocket like the petals of a flower, cooled to 40 degrees above absolute zero, parked 1.5 million kilometers from Earth so that nothing between it and the sky could blur what it saw. It was pointed at the exact stars at the center of the disagreement. It did not settle the argument. In 2023, the Webb telescope returned its measurements of those stars. They confirmed that the Hubble Space Telescope had been reading them correctly for more than a decade. The instrument that was supposed to find the mistake found no mistake. The gap between the two clocks did not close, it hardened. That is where cosmology is standing tonight. Not at a mystery it has not yet looked into, at a mystery it has looked into with the best eyes it has ever built, and found looking back. Hello, and welcome to Sidereal. If you find this kind of slow exploration useful for sleep or for winding down, a like or a subscribe genuinely helps this channel. And I am curious where you are listening from. Drop your location and your local time in the comments. Tonight the question is this: two measurements, made by two entirely separate methods, by two sets of scientists who have spent their careers checking each other's work, disagree about how fast the universe is expanding. Both are precise to within about 1%. Both are almost certainly not wrong in any ordinary sense, and they cannot both be right. Over the next few hours, we are going to walk the whole length of both chains. Every rung, every calibration. The pigeons in the horn antenna in New Jersey. The woman at Harvard who found the first rung and was paid 30 cents an hour to do it. The water molecules orbiting a black hole 23 million light-years away that anchor the modern ladder. The helium flash inside a dying star that gives us a second, independent ruler. And at the end of it, honestly, what remains unexplained. Let us begin with the two numbers themselves. The first is called the early universe measurement. It comes from the cosmic microwave background, the afterglow of the hot beginning, mapped across the whole sky by the European Space Agency's Planck satellite. From that ancient light, cosmologists extract a number describing how fast the universe ought to be expanding today, provided that our standard model of physics holds all the way from the beginning until now. That number is 67.4 kilometers per second per megaparsec. The second is called the late universe measurement. It is built by a team called SHOES, led by the Nobel laureate Adam Rees at Johns Hopkins University in Baltimore. It assumes nothing at all about what the universe looked like in its infancy. It works outward from stars we can actually see, climbing a ladder of distance from our own galaxy to others, using pulsating stars and exploding stars to calibrate the expansion directly. That number is 73 kilometers per second per megaparsec. The gap between them is about 9%. 9% sounds forgiving. In ordinary life, 9% is the difference between £100 and 109. It is a rounding error on a mortgage. In cosmology, it is 1 billion years of history. The early universe number gives the age of the cosmos as roughly 13.8 billion years. The late universe number gives closer to 12.8 billion. We do not know when everything started to within 1 billion years, and the uncertainty is not because our instruments are crude. It is because our instruments are excellent, and they disagree. If the gap were an error inside one machine, better machines should have shrunk it. That is the ordinary way these things resolve. A discrepancy appears, the data improves, the discrepancy dissolves, and nobody writes a book about it. This one has done the opposite. Every improvement in precision on either side has made the gap statistically worse, because the uncertainties have collapsed while the central values have stayed exactly where they were. There is a threshold in physics called 5 sigma. It is the point at which the odds of a result being a statistical accident fall below about 1 in 3.5 million. When a particle physics experiment crosses 5 sigma, the field calls it a discovery, and somebody usually opens something expensive. The disagreement between these two measurements crossed 5 sigma around 2019. So there is a discovery here. It is simply not the kind anyone applied for funding to make. The discovery is not a new particle or a new force. The discovery is that we do not understand the expansion of the universe. Before going further, it is worth being precise about what expansion actually is, because almost every intuitive picture of it is wrong in a way that matters for everything that follows. Expansion is not galaxies flying apart through space like fragments from an explosion. There is no center that everything is flying away from. There is no edge that things are flying toward. The galaxies were not given an initial shove and left to coast. What is happening is that the space between them is growing. New space appears everywhere, at all times, at the same rate in every direction. If you could somehow mark 2 points in genuine vacuum, with nothing between them at all, and come back much later, the distance between those marks would have increased. Nothing pushed them apart. The geometry between them changed. This is difficult to hold, because nothing in ordinary life behaves this way. When you stretch a rubber band, the rubber thins. There is a fixed amount of material being pulled over a longer distance. Space does not thin, it simply becomes more of itself. Galaxies are not glued to a sheet that is being pulled taut. They sit in a coordinate grid that is quietly getting larger underneath them. Light traveling through that growing space is stretched with it. A photon emitted from a distant galaxy as blue light arrives here with its wavelength lengthened, shifted toward the red end of the spectrum. That is what redshift means in cosmology. It is not the Doppler effect of something rushing away from us. It is the accumulated stretching of the space the light crossed on the way here. The light carries a record of how much the universe grew during its journey. The number that describes how fast that growth is happening is called the Hubble constant. The name is a historical accident, and it is doubly misleading, because the constant is not constant, and Hubble was not the first to find it. In 1929, Edwin Hubble published a short paper at the Mount Wilson Observatory in California, showing that the recession velocities of galaxies increased in proportion to their distance. The further away a galaxy was, the faster it appeared to be receding. He was building on measurements he had not made himself. The distances came from pulsating stars whose behavior had been catalogued by Henrietta Leavitt at Harvard 2 decades earlier. The velocities came largely from Vesto Slipher at the Lowell Observatory in Arizona, who had spent years coaxing spectra out of faint spiral nebulae, and from Milton Humason, a former mule driver at Mount Wilson, who had taught himself to be one of the finest observers of his generation. Hubble's value for the constant was about 500 kilometers per second per megaparsec, roughly 7 times larger than anything we would accept today. His relationship was real. His scale was badly wrong. The stars he was using were closer and intrinsically brighter than he believed, and the error propagated straight through into the number. Hubble himself was careful about what he claimed. He described a relationship between distance and redshift. He did not, in that paper, say the universe was expanding. The Belgian priest and physicist Georges Lemaitre had already derived precisely that 2 years earlier, in 1927. Working directly from Einstein's equations of general relativity, he published it in a French-language journal in Brussels that almost nobody outside Belgium read. He estimated a constant of about 600 kilometers per second per megaparsec. In private correspondence, he referred to the beginning as fireworks. Later, he called the initial state the primeval atom. His paper was the true beginning of modern cosmology, and for several decades it was Hubble whose name went on to the constant. And the constant is not constant. It changes with time, which means the phrase Hubble constant is shorthand for the value of the expansion rate right now, in our own epoch, in our local patch. In the first few 100,000 years, the expansion was enormously faster. Then gravity spent billions of years slowing it down. Then, roughly 5 billion years ago, something reversed that trend, and the expansion began to accelerate. We call the cause dark energy, which is a name and not an explanation. So the number we are chasing is a snapshot of a process that has been running and changing for almost 14 billion years. It is worth knowing that this is the second time the value of this number has been the subject of a long and rather bad-tempered disagreement. For most of the second half of the 20th century, two camps argued about it, and the gap between them was not 9%. It was a factor of 2. Alan Sandage, who had been Hubble's assistant at Mount Wilson and inherited his program, spent decades arguing for a value around 50. Gerard de Vaucouleurs at Texas argued, with equal conviction and equally serious data, for around 100. Each thought the other's distance calibrations were badly wrong. The argument ran for 30 years and became sufficiently entrenched that a great deal of published cosmology simply carried the uncertainty forward as an unresolved factor rather than committing to a number. That fight was eventually settled by better instruments, specifically by the Hubble Space Telescope, which is why measuring this quantity was one of the 3 original justifications for building it. So the field has been here before, and the historical precedent points in a reassuring direction. A long disagreement about the expansion rate, resolved by a better telescope. That precedent is what makes the current situation genuinely strange. We built the better telescope. We pointed it at the disputed objects. It did not resolve anything. The reason the exact value matters so much is that it sets the scale of everything else in cosmology. If you know the Hubble constant, you know the distance to any galaxy whose redshift you can measure. You know the age of the universe. You know how much dark energy there has to be to produce the acceleration we observe. You know the physical size of the largest sound wave that could have crossed the early plasma before it cleared. Change the number by 9%, and every one of those quantities moves. The age shifts by 1 billion years. The dark energy budget shifts. The timeline of how structure assembled itself when the first galaxies could have formed. How long they had to grow shifts with it. Here is one way to feel how small the underlying effect is, and how strange it is that we can measure it at all. Take the distance between the Earth and the Sunday. Shrink it to 1 millimeter, about the thickness of a stack of 10 sheets of paper. On that scale, the nearest star, Proxima Centauri, sits 260 meters away. The center of our own galaxy is about 1,600 kilometers away. The Andromeda Galaxy, our nearest large neighbor, is roughly 2,500 kilometers off, and the expansion of the universe, acting across that entire gap, adds less than 1 millimeter per second to the separation. Less than the width of a human hair per second, across 2,500 kilometers. That is the signal. It is measured to better than 1% by 2 different methods, and the 2 methods do not agree. The reason it is measurable at all is that the effect accumulates. Over a few million light years, it is nothing swamped completely by ordinary gravity, which is why Andromeda is in fact falling toward us rather than receding. Push out to a few 100 million light years, and expansion begins to dominate over local gravitational tugs. Push out to the edge of what we can see, and it becomes the dominant fact about the universe, with the most distant galaxies receding faster than light can travel toward us, their photons stretched so far into the infrared that only an instrument like the Webb telescope can register them. Now, the 2 numbers come from 2 entirely different ways of getting at that history, and it is worth stating plainly, at the start, what the crucial asymmetry between them is. The early universe measurement does not measure the expansion rate, it infers it. What the Planck satellite actually measures is a pattern of hot and cold spots across the sky, and the characteristic angular size of the features in that pattern, how large they appear from here. To turn an angular size into a distance, you have to know the true physical size of the thing you are looking at, and the true physical size of that feature is not observed. It is calculated from a model of what the early universe was made of and how it behaved in its first 380,000 years. That calculation is superb. It is built on well-tested nuclear and atomic physics, and it produces a picture that fits thousands of independent data points across the whole sky. But it is a calculation. It answers the question, given that our model of the beginning is complete, what must the expansion rate be today? The late universe measurement asks a different question. It asks, what is the expansion rate, measured directly, using objects we can point at? 2 questions. If the model of the beginning is complete, they have the same answer. They do not have the same answer. To begin at the beginning, we have to go back to a hiss. In 1964, 2 radio astronomers at Bell Telephone Laboratories in Holmdel, New Jersey, were trying to get a piece of equipment to behave. The equipment was a horn-shaped antenna about 6 meters long, built like a great metal ear cocked at the sky. It had been designed for a genuinely commercial purpose to catch radio signals bounced off the Echo balloon satellites, which were essentially enormous reflective balloons put into orbit, so that signals could be skipped off them from one side of a continent to the other. By 1964, that job was finished. The antenna was free. Arno Penzias and Robert Wilson wanted to use it for radio astronomy. Both were young. Both understood that they had access to one of the quietest, best-calibrated receivers on Earth, and both wanted to point it at the sky and measure faint sources properly, which meant first accounting for every scrap of noise in the system so that whatever was left over could be trusted. There was noise left over. It would not go away. It was small equivalent to a signal from something at a temperature of about 3.5 degrees above absolute zero. It was steady. It did not vary with the time of day, which ruled out the Sunday. It did not vary with the season, which ruled out anything tied to Earth's position in its orbit. And, most awkwardly of all, it came from every direction they pointed. They swung the horn toward New York City, thinking urban radio interference. The noise was the same. They swung it at empty sky. The same. They cooled the receiver itself with liquid helium to 4 degrees above absolute zero, so that the instrument's own thermal chatter could not be blamed. The noise remained. They took the antenna apart. They found that a pair of pigeons had been roosting inside the horn and had coated the interior with what Penzias later described, in a phrase that has followed the story ever since, as a white dielectric material. They evicted the pigeons. They cleaned the horn. They taped over the riveted joints in case the seams were leaking. The pigeons came back and had to be dealt with a second time, less gently. The noise remained. For most of a year, 2 careful people assumed they had a broken instrument. They were, in fact, listening to the oldest thing there is. About 60 kilometers away, at Princeton University, a group led by Robert Dick had spent that same period working on the other side of the problem. Dick, along with Jim Peebles, Peter Roll, and David Wilkinson, had reasoned that if the universe began in a hot, dense state, the radiation from that state should still be here cooled and stretched by the expansion of space into the microwave band, filling everything, arriving from all directions at a temperature of a few degrees above absolute zero. Roll and Wilkinson were building a small antenna on the roof of the physics building to look for it. They were not the first to work this out. In 1948, Ralph Alpher and Robert Herman, working with George Gamow, had published a prediction that the leftover radiation should be around 5 degrees above absolute zero. The prediction sat in the literature for 16 years, and essentially nobody acted on it. It was regarded as an interesting consequence of a speculative model, not as a target you could go and hit. A mutual colleague made the connection. Penzias telephoned Dick. Dick listened, put the phone down, turned to his group and told them, in one of the most quietly devastating sentences in the history of science, that they had been scooped. The 2 teams published back-to-back in 1965. Penzias and Wilson wrote a short, cautious paper describing an excess antenna temperature and offering no cosmological interpretation whatsoever. Dick's group wrote the companion paper explaining what it meant. Penzias and Wilson received the Nobel Prize in Physics in 1978. Dick did not. Alpha and Herman did not. What that measurement ended, more or less immediately, was a serious scientific argument that had been running for 2 decades. Through the 1950s, the hot beginning model had a genuine rival. The steady-state theory, developed by Herman Bondi, Thomas Gold, and Fred Hoyle at Cambridge, proposed a universe that expands but does not evolve, one in which matter is continuously created at an extremely low rate, filling in the gaps as space grows, so that the average density stays constant forever. It had no beginning and required none. It was elegant, it was testable, and its supporters included some of the most capable physicists of the era. Hoyle, in particular, was not a marginal figure. He worked out, with William Fowler and Margaret and Geoffrey Burbidge, how essentially every element heavier than helium is manufactured inside stars, one of the great results of 20th century physics, and the reason the carbon in your hands has a known origin. He was also the person who, during a radio broadcast in 1949, referred dismissively to the rival idea that everything had started in one big bang. He meant it as a criticism. The name stuck to the theory he was arguing against and has never come off. The steady-state universe cannot produce a microwave background. There is no early hot, dense phase to leave one behind. Once the radiation was measured, and measured to be uniform in every direction, at a temperature nobody could account for any other way, the argument was effectively over. Hoyle spent the rest of his career proposing modifications and never accepted the conclusion. There is a detail in the microwave background that took another 2 decades to nail down properly, and it is one of the stranger facts in observational astronomy. The radiation is not perfectly uniform, and the largest departure from uniformity has nothing to do with the early universe at all. One half of the sky is very slightly hotter than the other, by about 1 part in 1,000, which is 100 times larger than the primordial fluctuations underneath it. The pattern is a simple gradient, hot in one direction and cold in the opposite one. It is a Doppler shift. We are moving. Because the radiation fills all of space and is at rest relative to the bulk of the matter in the universe, it defines something that Einstein's relativity is often said to forbid. Not an absolute rest frame, but a preferred one, a frame in which the universe as a whole is not going anywhere. Motion relative to that frame is detectable. Move toward a patch of sky, and the radiation arriving from ahead is blue-shifted and appears hotter. The radiation from behind is red-shifted and appears cooler. Measure the gradient, and you get your velocity. The solar system is moving at about 370 kilometers per second relative to the cosmic microwave background. Subtract the sun's orbit around the galaxy and the galaxy's motion within the local group, and the local group as a whole is moving at about 620 kilometers per second toward a region in the direction of the constellations Centaurus and Hydra, a concentration of mass known as the Great Attractor, which sits behind the plane of our own galaxy and is therefore extremely awkward to observe directly. You are, at this moment, being carried in that direction at over 600 kilometers per second. Nothing about it is perceptible. There is nothing to feel it against, and no window to see it through. It was determined by mapping a temperature difference of a few thousandths of a degree across the sky. That dipole has to be measured and removed before anything else in the map can be read, which is why it took careful instruments to see past it to the pattern underneath. What they had found is now called the cosmic microwave background, and its physical presence is worth sitting with for a moment, because it is easy to file it away as a distant object, and it is not one. You are lying in the dark. The room is quiet. Around you, passing through the walls, through the ceiling, through the mattress, and through your body, without interacting with any of it, are photons that have been traveling since before there were atoms, before there were stars, before there was anything in the universe with a shape. There are roughly 410 of them in every cubic centimeter of space, which means there are trillions in the room with you, and there is no way to be anywhere they are not. If you found an old analog television, unplugged the aerial and tuned it between channels, a small fraction of the static on the screen would be them. They are not arriving from a place. They are arriving from a time. Here is what happened at the moment they were released. For the first 380,000 years, the universe was too hot for neutral atoms to exist. Every time an electron and a proton came close enough to bind, a photon with enough energy came along and knocked them apart again. So matter existed as a plasma-free electrons and free nuclei, moving in a sea of light. And a free electron is extremely good at scattering photons. Light could not travel more than a short distance before being deflected. The universe was opaque in the way that the inside of a cloud is opaque. Not dark, but impossible to see through. Brilliantly lit and completely featureless. Then the universe expanded, and expansion cools things, and the temperature dropped below about 3,000 degrees. At that point, the typical photon no longer had enough energy to break a hydrogen atom apart. Electrons and protons combined and stayed combined. Cosmologists call this recombination, which is a slightly odd name, since nothing was combining for a second time. The free electrons disappeared into atoms. The thing that had been scattering the light was gone, and every photon that was in mid-flight at that moment suddenly found that there was nothing in front of it. They have been flying ever since. 13.8 billion years, uninterrupted. Along the way, the expansion of space stretched their wavelengths by a factor of about 1100, dragging them out of the visible band, through the infrared, into the microwave. What was released as a fierce orange glow arrives here as a cold whisper at 2.725 degrees above absolute zero. Recombination did not happen instantaneously, and the reason is a detail that turns out to matter for the precision of everything built on it. There are enormously more photons than atoms in the universe, about 1.5 billion photons for every proton, which means that even after the average photon had dropped below the energy required to ionize hydrogen, there were still, in the far tail of the distribution, plenty of photons energetic enough to do it. A 1,000,000,000 ratio means the tail is very well populated. So the universe had to cool considerably further than a naive calculation suggests before the last of those energetic photons became too rare to matter. Recombination is usually quoted as happening at a temperature around 3,000 degrees, when the naive estimate would have put it nearer 12,000. The delay is caused entirely by the photon-to-baryon ratio, and the process took tens of thousands of years to complete rather than happening at an instant. So the surface we observe is not infinitely thin. It has a depth, a period during which photons were progressively less likely to be scattered again. That thickness smooths out the smallest features in the pattern, which is exactly the damping at small angular scales visible in the graph of the acoustic peaks, and which itself carries information. When we look at the cosmic microwave background, we are looking at a surface, not a physical surface, nothing is there, but a surface in time. It is the last place a photon could have been scattered before the universe cleared. And it is called, precisely and rather beautifully, the surface of last scattering. It surrounds us in every direction, because in every direction we are looking back to the same moment. Someone in a galaxy 10 billion light-years from here sees their own version of it, centered on themselves. The surface is not a wall around the universe. It is the horizon of what light can carry to any given observer. And this is where that ancient light stops being merely evidence that the beginning happened and starts being an instrument. The plasma before recombination was not perfectly smooth. It was very nearly smooth. The variations were about 1 part in 100,000, but not exactly. There were regions where the density was fractionally higher and regions where it was fractionally lower, seeded by processes in the first fraction of a second that we still do not fully understand. In those slightly denser regions, gravity pulled matter inward. But the matter was tangled up with the light, and light exerts pressure. As the gravity compressed a region, the photon pressure inside it rose and pushed back out. The region overshot, rarefied, and gravity began pulling it back in again. That is an oscillation. The early universe was ringing. These were real sound waves, genuine pressure waves moving through a genuine medium, at a speed of roughly 58% of the speed of light, which is what the speed of sound becomes in a fluid made mostly of radiation. The universe spent its first 380,000 years filled with a sound too low and too vast to be described as a note, propagating through a plasma the temperature of the surface of a star. And then the plasma vanished. Recombination did not fade the sound out. It removed the medium. The photons decoupled from the matter. The pressure that had been driving the oscillations disappeared, and every wave froze exactly where it was in its cycle. Some regions were caught at maximum compression, some at maximum rarefaction. Some had not yet had time to finish a single cycle. The light that escaped carried the imprint. Compressed regions were slightly hotter, rarefied regions were slightly cooler. That pattern of hot and cold spots is what the Planck satellite mapped across the whole sky, and it is a photograph of a sound, taken at the instant the sound stopped. The temperature differences involved are around 1 part in 100,000, a few tens of millionths of a degree. That is the precision required to see the pattern at all, and it is the reason the first map of it did not arrive until 1992, 28 years after Penzias and Wilson first noticed something wrong with their antenna, there is one number hidden inside that frozen pattern that matters more than all the others for tonight's story. There is a limit to how far a pressure wave could have traveled between the beginning and the moment the plasma cleared. It is set by the speed of sound in that plasma and the amount of time available. Waves larger than that limit never got the chance to complete a compression. Waves smaller than it went through several cycles. And right at that boundary sits the largest wave that had exactly enough time to compress once, and no more, before it was frozen in place. That distance is called the sound horizon. And because it has a definite physical size that can be calculated from the physics of the plasma, it functions as a ruler, an object of known length, sitting at a known moment in the past, visible from here. Measure how large that ruler appears on the sky. Compare it with how large it actually is, and you have the distance to the surface of last scattering. From that distance, and a model of how the universe has expanded since, you can extract the expansion rate today. That is the early universe clock. Everything it says about the Hubble constant rests on knowing the true length of that ruler. And the true length of that ruler is not measured, it is computed. Reading a ruler you cannot touch requires a particular kind of patience and 3 generations of instruments to do it. Start with what the pattern actually looks like when you measure it properly. Take a map of the whole microwave sky, with its hot and cold spots at the level of parts per 100,000, and ask a simple statistical question. At what angular scale are the temperature variations strongest? The blotches might typically be the size of the full moon on the sky, or 1/10 of that, or 100th. Plot the answer as a graph variation strength against angular scale, and you do not get a smooth, featureless curve. You get peaks. A tall one, at about 1 degree, roughly twice the width of the full moon. Then a smaller one at about half that scale. Then another, smaller still, then more, marching off toward finer and finer scales and gradually damping away. Those are the frozen sound waves, sorted by size. The first and tallest peak is the wave that had exactly enough time to compress once before the plasma cleared. The second peak is the wave that compressed, bounced back out, and was caught at maximum rarefaction. The third compressed, rarefied, and compressed again. They are harmonics, the overtones of a single instrument whose length was the sound horizon and whose playing time was 380,000 years. Every feature on that graph carries information. The angular position of the first peak tells you the geometry of space between here and there, whether light has traveled in straight lines or been bent by the overall curvature of the universe. When the peak was located precisely, it landed almost exactly where a flat universe predicts, which is how we know that space, on the largest scales, has no measurable curvature at all. The relative heights of the odd and even peaks tell you how much ordinary matter there is. Ordinary matter, protons and neutrons, what physicists call baryons, has mass, and mass makes the compressions deeper without making the rarefactions correspondingly shallower. So a universe with more ordinary matter has a taller first peak relative to the second. That ratio is one of the most precise measurements of the amount of normal matter in the universe, and it agrees to within a few percent with a completely independent number derived from the abundances of light elements forged in the first 3 minutes. 2 entirely unrelated pieces of physics, separated by 400,000 years, returning the same value for how much ordinary stuff exists. The overall height of the third peak is sensitive to dark matter, which has gravity but no pressure, and therefore deepens the wells without pushing back. And the way the peaks damp away at small scales tells you about the thickness of recombination, the fact that the plasma did not clear instantaneously, but over a period of tens of thousands of years, during which photons could diffuse out of small structures and smear them away. So the graph is not a curiosity. It is a readout of the contents of the early universe, and the argument of tonight's story lives inside it. Getting that graph took 30 years. The first all-sky map came from the Cosmic Background Explorer, launched by the American Space Agency on the 18th of November, 1989, from Vandenberg Air Force Base in California. It carried 3 instruments and a tank of liquid helium, and it had been 15 years in the making. It had originally been designed to launch from a space shuttle. After the loss of Challenger in 1986, the entire spacecraft had to be redesigned to fit on a Delta rocket instead. It did two things that mattered. The first was to measure the spectrum of the background radiation, not just its temperature, but the precise distribution of energy across wavelengths. If the radiation really was the cooled remnant of a hot, dense, thoroughly mixed early state, its spectrum should be a perfect blackbody, the specific mathematical curve that any object in thermal equilibrium emits. The instrument built to test this returned a match so exact that when John Mather presented the results at a meeting of the American Astronomical Society in 1990, the error bars were smaller than the thickness of the line drawn through the data, and the audience gave it a standing ovation. It remains one of the most precise agreements between prediction and measurement anywhere in physics. The temperature came out at 2.725 degrees above absolute zero. The second thing it did, announced in 1992, was to detect the variations. George Smoot's team found the temperature differences across the sky at the level of a few parts in 100,000, the first direct evidence of the seeds from which every galaxy would eventually grow. Mather and Smoot shared the Nobel Prize in Physics in 2006, but the explorer's angular resolution was 7 degrees. On that scale, you can see that variations exist. You cannot see the peaks. The whole acoustic structure lives at 1 degree and below, and it was entirely invisible to it. The next step was the Wilkinson Microwave Anisotropy Probe, named for David Wilkinson, one of the Princeton physicists who had been building a rooftop antenna to hunt for this radiation when Penzias called Dickie. He worked on the mission and died before its final results were published. The probe launched on the 30th of June, 2001, and traveled out to the second Lagrange point, a gravitationally convenient position 1.5 million kilometers from Earth on the far side from the Sun, where a spacecraft can shield itself from the Sun, Earth and Moon all at once, and stare at deep space in permanent cold. It operated for 9 years. Its resolution was 13 arc-minutes, roughly 30 times finer than its predecessor. It resolved the first and second acoustic peaks cleanly and caught the beginning of the third. From that data, it derived an expansion rate of about 70 kilometers per second per megaparsec, with an uncertainty of a few percent, 70, sitting almost exactly between the two numbers that would later refuse to meet, with error bars wide enough to be comfortable with either. At the time, that comfort read as agreement. In hindsight, it reads as a measurement that was not yet sharp enough to notice a problem. Then came Planck. The European Space Agency launched it on the 14th of May, 2009, on the same rocket that carried the Herschel Infrared Observatory. It went to the same second Lagrange point, the same gravitational parking spot where the Webb telescope now sits. Its specifications were a considerable step up. It observed in 9 frequency bands, from 30 GHz to 857 GHz. Its best angular resolution was 5 arc-minutes. Its detectors were cooled to 1/10 of a degree above absolute zero, making the instrument, for the duration of its mission, almost certainly the coldest known object of its size in the universe, colder than the space it was sitting in. The 9 frequency bands are not redundancy. They are the solution to the hardest practical problem in the field, which is that the microwave sky is not empty. Our own galaxy glows in the microwave band. Dust between the stars glows. Electrons spiraling in the galactic magnetic field glow. Distant galaxies full of star formation glow. All of this sits between us and the background, and all of it is brighter, in places, than the signal underneath. The trick is that these foregrounds have different spectra. Galactic dust brightens toward higher frequencies. Synchrotron emission from electrons brightens toward lower ones. The cosmic background has the flat blackbody signature of a fixed temperature. Observe the same patch of sky at 9 frequencies, and you can solve for which component is which and subtract them out. Building a foreground model good enough to trust at the level of millionths of a degree occupied hundreds of people for years, and it is the single largest source of systematic uncertainty in the final result. Planck also mapped something the earlier missions could not: the polarization of the light. Photons, scattering off electrons in a plasma that is being compressed, acquire a slight directional preference in their electric field. That polarization pattern carries independent information about the velocity of the plasma at the moment of last scattering, and it provides a cross-check on the temperature measurements that does not share their systematics. The final cosmology results, released in 2018, gave an expansion rate of 67.4 kilometers per second per megaparsec, plus or minus 0.5, half a kilometer per second per megaparsec, better than 1%, on a quantity describing the growth of the entire universe, derived from a temperature map accurate to millionths of a degree. And it is not a single measurement. It is the output of fitting one Model 6 free parameters, no more to thousands of independent data points spanning the whole sky and the whole range of angular scales. 6 numbers: the density of ordinary matter, the density of dark matter, the age of the universe at recombination, the amplitude and tilt of the primordial fluctuations, and the optical depth from later reionization. Adjust those 6, and you can reproduce every peak, every trough, every damping detail, and the polarization pattern on top of it. One of those 6 parameters deserves a moment on its own, because it is the only one that concerns something that happened long after the light was released. It is called the optical depth to reionization, and it accounts for the following. The universe went transparent at 380,000 years and stayed transparent through a long stretch that cosmologists call the Dark Ages, during which there was nothing luminous in it at all, just cooling neutral hydrogen and the gradually strengthening gravitational wells where structure was assembling. Then, somewhere between roughly 200 million and 1 billion years, the first stars and the first quasars switched on, and their ultraviolet light began stripping electrons off the hydrogen again. That reionized the universe, and free electrons scatter photons. So a fraction of the microwave background photons, around 5%, were scattered on their way here, long after their release, by electrons liberated by the first generation of stars. That scattering slightly blurs the pattern and slightly polarizes it, and the amount of blurring tells you when reionization happened. It is a strange thing to be able to extract from a temperature map. The light from before the first stars carries a faint watermark left by the first stars, and by measuring the watermark, you can date an era from which we have almost no other direct evidence at all. The residuals, the differences between what the model predicts and what the sky shows, point by point, are consistent with random noise. That is the thing about the early universe measurement that is genuinely hard to argue with. If the model was substantially wrong, that quality of agreement across that many independent measurements would be an extraordinary coincidence. The Planck cosmology analysis was led by people including George Efstathiou at Cambridge, Jean-Luc Puget, and François Boucher in France. Their approach to the error budget was close to obsessive. They tested the data against every systematic they could name, and then against systematics they invented in order to rule them out. There is one further check on the ruler that deserves its own space, because it addresses the most obvious objection to everything above. If the sound horizon is calculated rather than observed, is there any way to see it directly? There is, and it comes from an entirely different kind of survey. Go back to the frozen sound waves. At recombination, the photons streamed away and the pressure vanished, but the matter did not disappear. Each initial overdensity had been sitting at the center of an outgoing spherical pressure wave, and when the wave stalled, it left the ordinary matter piled up in a shell at a fixed radius around that center, with dark matter still concentrated in the middle. Both then acted as seeds for galaxy formation, which means that in the distribution of galaxies today, there should be a slight statistical preference for finding pairs of galaxies separated by exactly that distance. The sound horizon, stretched by all the expansion since, not a ring you could see by eye. A faint excess in the statistics of order 1%, buried in a distribution that otherwise looks like filaments and voids. It is called the Baryon acoustic oscillation feature, and it was first detected in 2005 in data from the Sloan Digital Sky Survey and the 2-degree Field Galaxy Redshift Survey by teams working independently. Finding a 1% statistical bump requires an enormous number of galaxies, precisely measured across a very large volume. The measured scale is about 147 megaparsecs, roughly 480 million light-years, and it matches what the microwave background analysis says it should be. That is a genuinely important confirmation. The same physical ruler, laid down at recombination, seen in two completely different ways. Once as a temperature pattern in ancient light, and once as a preferred separation between galaxies billions of years later. It establishes that the sound horizon is a real feature of the universe and not an artifact of how the microwave data is processed. What it does not do, and this is the part that matters for tonight, is tell you the ruler's length in kilometers independently of the physics used to calculate it. The galaxy surveys measure the ruler in angles and redshifts, just as the microwave background does. They confirm that the ruler exists and that its apparent size behaves consistently across cosmic time. They inherit the same assumption about its true physical length. So the two are not independent in the way one would want. If the early universe contained something that shortened the sound horizon, both measurements would shift together and neither would notice. The obvious next worry is that a satellite could have one specific flaw that nobody caught. That worry has been closed off by ground-based instruments that share nothing with it. The Atacama Cosmology Telescope is a 6-meter dish sitting at an altitude of over 5,000 meters on Cerro Toco in the Chilean Atacama, one of the driest places on the planet, because water vapor in the atmosphere absorbs microwaves, and the only way to reduce it is to get above most of it. It surveys smaller patches of sky than Planck. At higher resolution, its recent data gives an expansion rate of about 67.9 with an uncertainty near 1.5. The South Pole Telescope operates at the Amundsen-Scott Station in Antarctica, where the atmosphere is thin, extremely dry, and unusually stable, and where the same patch of sky stays available continuously for months. It gives 68.8 with a similar uncertainty. Different continents, different mirrors, different detector technologies, different analysis teams with different software, different assumptions about the atmosphere, and considerable professional incentive to disagree with each other. They all land in the high 60s, which brings us to the caveat that everything after this point turns on, and it needs stating without hedging. Every one of those numbers is the answer to a conditional question. The microwave background does not hand over an expansion rate. It hands over an angular scale, how big the acoustic features appear on the sky. Converting that angle into a distance requires knowing the true physical length of the sound horizon. And the sound horizon is not observed. It is calculated from the density of ordinary matter, the density of dark matter, the density of radiation, and the rate at which the universe was expanding during the first 380,000 years. If any ingredient in that recipe is wrong, if the early universe contained a component we have not accounted for, or expanded on a slightly different schedule than we assume, then the ruler is a different length than we think, and every distance measured with it is wrong by the same factor. And so is the expansion rate that comes out at the end. This is not a flaw in the method. It is the method, and the method's power comes from exactly this feature. It fits everything at once and produces a single coherent picture of the universe from a handful of numbers. But it means that 67.4 is not a raw reading off a dial. It is what the universe must be doing today, if our account of its first 400,000 years is complete. For most of 2 decades, that conditional caused nobody any difficulty, because there was no reason to doubt the account. Then somebody built a clock that did not need it. The second clock does not look back to the beginning. It does not need a model of the first 380,000 years, or a recipe for the early plasma, or any assumption about what the universe contained before there were stars. It starts here, with light arriving at telescopes tonight, and works outward step by step. It begins with a woman in a room full of glass plates. Henrietta Leavitt was born in Lancaster, Massachusetts, in 1868, the daughter of a congregational minister. She studied at Oberlin College, and then at what was then called the Society for the Collegiate Instruction of Women, which would later become Radcliffe College, graduating in 1892. In her final year, she took a course in astronomy and did well in it. Shortly afterwards, she developed an illness that left her seriously deaf for the rest of her life. In 1895, she began working at the Harvard College Observatory as a volunteer. In 1902, she was hired onto the permanent staff at 30 cents an hour. She was one of a group of women that the observatory's director, Edward Pickering, had assembled to do the work of measuring photographic plates. They were called computers, which at the time was a job description rather than a machine. Pickering's motives were a mixture of the progressive and the frankly economic. He had a vast and growing archive of photographic plates and no budget to hire men to process them, and educated women could be employed for a fraction of the cost. Whatever the reasoning, the result was that a substantial fraction of the fundamental observational astronomy of that era was carried out by women who were not permitted to operate the telescopes that produced their data. Williamina Fleming, who had come to the Pickering household as a maid, went on to classify more than 10,000 stars and to discover the Horsehead Nebula. Antonia Maury developed a stellar classification scheme so subtle that it took decades for the field to understand what she had found. Annie Jump Cannon, who was also deaf, classified around 350,000 stars by hand and produced the spectral sequence that every astronomy student still memorizes today. Leavitt was assigned to variable stars. Specifically, she was given the plates of the Magellanic Clouds, two small satellite galaxies of the Milky Way, visible only from the southern hemisphere, which the observatory had been photographing for years from its station at Arequipa in Peru. Her job was to find stars in those plates, whose brightness changed over time, and to characterize them: how bright, how faint, how long the cycle took to repeat. The work required comparing plates of the same field taken on different nights, star by star, looking for the ones that had shifted in brightness. There were hundreds of plates. Each contained thousands of stars. She did it by superimposing a negative of one plate on a positive of another, so that anything unchanged cancelled out and anything variable stood out. It is worth understanding what that actually involved, physically, because the description makes it sound more automated than it was. The plates were glass, coated with photographic emulsion, roughly 20 centimeters square. Each one recorded a patch of southern sky as it had appeared on one night in Peru, and each contained tens of thousands of star images as small black dots of varying size, larger dots for brighter stars, since brightness on a photographic plate registers as the extent of the exposed grain rather than its darkness. To find a variable, you compared two plates of the same field taken at different times. Superimpose a glass positive of one onto a glass negative of the other. Hold them up to a light, and every unchanged star cancels itself out into gray. What survives is anything that moved or changed brightness. Then you measured the survivors. Estimating a star's magnitude meant comparing the size of its dot against a calibrated sequence of reference dots by eye through an eyepiece, and recording the estimate in a ledger. Then you did it again on the next plate, and the next, until you had enough points to reconstruct a light curve. There were no calculating machines for any of this. The arithmetic was done on paper. By 1908, she had catalogued 1,777 variable stars in the Magellanic Clouds. That number alone would have been a career. It is not what she is remembered for. Among those variables was a particular class known as Cepheids, named after Delta Cephi, the prototype in the constellation Cepheus, whose variability had been noticed by John Goodricke in 1784. Goodricke was also deaf and died at 21, and had by then worked out both the existence of eclipsing binary stars and the regular pulsation of Delta Cephi. A Cepheid does not flicker, it breathes. The mechanism was worked out by Arthur Eddington and is worth following because it explains why the relation exists at all, rather than being a lucky empirical coincidence. In the outer envelope of these stars is a layer of helium that is partially ionized, some of its electrons stripped, some still attached. That layer has an unusual property. When it is compressed and heated, the extra energy does not raise its temperature much, because the energy goes into stripping more electrons instead, and a more ionized gas is more opaque. So, the star contracts. The helium layer compresses, becomes more ionized, becomes more opaque. Radiation streaming outward from the core can no longer get through it easily and is trapped underneath. Pressure builds. The trapped pressure pushes the outer layers of the star outward. The star expands. The helium layer cools. Its electrons recombine. It becomes transparent again. The trapped radiation escapes. The pressure drops, and gravity pulls the envelope back down. Then it happens again. Eddington called it a valve. It is a heat engine with a star wrapped around it, and it will keep running as long as the star's structure keeps the ionization layer at the right depth. When conditions drift out of range, the pulsation stops, and the star leaves what astronomers call the instability strip. The reason the period predicts the luminosity is that both are set by the same thing: the size of the star. A larger, more luminous star has a lower average density, and the natural oscillation time of a self-gravitating sphere depends on its density. Bigger and sparser means slower. It is not far from the reason a large bell rings at a lower pitch than a small one. So the result is a rhythm, a swelling and shrinking of the entire star, with a period of anywhere from a day to several months. Absolutely regular, running like a metronome for as long as the star stays in that phase of its life. Delta Cephei itself swells and contracts by about 10% of its radius every 5 days and change, and has been doing so since long before anyone noticed. Leavitt noticed something about the ones in the small Magellanic Cloud. The brighter a Cepheid appeared, the longer its cycle took. This is not obvious, and it is not trivial. Ordinarily, comparing the apparent brightness of two stars tells you nothing about them, because you do not know how far away either one is. A dim star nearby and a brilliant star far away look identical from here. That ambiguity is the fundamental obstacle in all of astronomy, and it is why measuring distance is difficult in a way that measuring almost anything else is not. But every star in the small Magellanic Cloud is at essentially the same distance from us. The cloud is far enough away that its own depth is small compared with its distance. So within that one population, the ambiguity vanishes. If one of those Cepheids looks 4 times brighter than another, it genuinely is 4 times more luminous. The comparison is fair. What Leavitt had found, therefore, was not a relationship between apparent brightness and period. It was a relationship between true luminosity and period. And a relationship like that turns a Cepheid into a distance marker anywhere in the universe. The logic runs like this: find a Cepheid, watch it for a few weeks, and time its cycle. The period tells you how luminous it truly is. Compare that with how bright it appears from here. The difference between how much light it emits and how much light arrives is caused entirely by distance, and the relationship is simple. Geometry brightness falls off as the square of the distance. Solve for the distance. She published the observation in 1908 in a paper on the Magellanic variables in 2 sentences that read almost as an aside. She returned to it properly in 1912 in a short circular from the observatory titled "Periods of 25 Variable Stars in the Small Magellanic Cloud." The circular was signed by Edward Pickering. The first line states that it was prepared by Miss Leavitt. 25 stars, 3 pages. It is one of the most consequential documents in the history of astronomy, and it contains the sentence that a remarkable relation had been noticed between the brightness of these variables and the length of their periods. Within a decade, the consequences began to arrive. Ejnar Hertzsprung and Harlow Shapley worked on the problem of calibration of tying Leavitt's relative scale to an absolute one. Shapley then used Cepheids and related variables to map the distribution of globular clusters around the Milky Way, and in 1918 concluded that those clusters were not centered on the Sunday. They were centered on a point, tens of thousands of light-years away, in the direction of Sagittarius. The galaxy was far larger than anyone had assumed, and the solar system was nowhere near the middle of it. Then Edwin Hubble, in 1923, found a Cepheid on a photographic plate of the Andromeda Nebula. He had been looking for novae. He marked the star on the plate with the letter that stood for nova, then crossed it out and wrote the abbreviation for variable instead, and added an exclamation mark. The plate survives. The correction is still visible on it. Timing that star's period gave its luminosity, which gave its distance, and the distance came out so vast that Andromeda could not possibly be inside our galaxy. It was a galaxy of its own. That single measurement settled an argument that had become, by then, quite heated. In April 1920, at the Smithsonian Museum of Natural History in Washington, Harlow Shapley and Heber Curtis had appeared on the same program to debate the scale of the universe. It has been known ever since as the Great Debate, which somewhat overstates its drama. It was 2 presentations and a discussion, and both men were polite. But the question was real, and the 2 positions were incompatible. Shapley argued that the Milky Way was enormous, far larger than previously thought, and that it constituted essentially the whole universe. The spiral nebulae in this picture were nearby clouds of gas within it. Curtis argued that the Milky Way was smaller than Shapley claimed, and that the spirals were separate galaxies at vast distances, island universes, in the phrase of the period. Each was right about half of it. Shapley was correct about the size of our galaxy and the Sun's position away from its center. Curtis was correct about the spirals. Neither had the evidence to settle the other half, because the evidence required a distance measurement to a spiral, and nobody had one. 3 years later, Hubble found his variable star on the Andromeda plate, and the question was over. There is something worth pausing on in the shape of that. The debate could not be resolved by argument, and both participants were experienced observers, reasoning carefully from real data. What resolved it was a single star in a single galaxy, whose period could be timed, and the rule that let its period be converted into a distance had been published 11 years earlier by someone who was not invited to the debate and was, at the time it took place, in the final year of her life. 6 years after that, Hubble used the same technique, extended to more galaxies, to find the relationship between distance and redshift. Every one of those results rests on the relation Leavitt found in a set of plates from Peru. She did not see most of it. She spent much of her career in poor health, and periods of illness took her away from the observatory for months at a time. She died of cancer on the 12th of December, 1921, at the age of 53, in Cambridge, Massachusetts, and was buried in the family plot. In 1925, the Swedish mathematician Gösta Mittag-Leffler wrote to the Harvard Observatory intending to nominate her for the Nobel Prize in Physics. The reply informed him that she had been dead for 4 years. The prize is not awarded posthumously, and so the matter ended there. There is a version of this story that treats the ending as an injustice to be indignant about, and the indignation is not wrong, but it is also not the interesting part. The interesting part is what the relation actually is, and how long it took to become trustworthy. Because a period luminosity relation is not, by itself, a distance ladder. It is a rule that says a Cepheid with a 10-day period is a certain number of times more luminous than a Cepheid with a 3-day period. That is a relative statement. To get an actual distance in kilometers or light years, you have to know the absolute luminosity of at least one Cepheid, measured by some method that does not itself depend on assumptions about stars. That is the calibration problem, and it turns out to be the hardest single problem in the entire chain. A century of work has gone into it. Almost every serious question about tonight's disagreement eventually reduces to some version of it. There is one more complication, and it matters enormously later, so it is worth putting on the table now. The relation is not perfectly universal. A Cepheid's luminosity at a given period depends slightly on its chemical composition, specifically on the abundance of elements heavier than helium, which astronomers unhelpfully call metals, meaning everything from carbon to uranium. Metal content affects the opacity of the star's outer layers, which affects the pulsation, which affects the relationship between period and brightness. Cepheids in the small Magellanic Cloud have noticeably fewer heavy elements than Cepheids in the Milky Way, which have fewer than Cepheids in the inner regions of large spirals. So the rule has a correction term, and the correction term has to be measured, and measuring it requires exactly the kind of independent distance information that you were using the Cepheids to obtain in the first place. There is also dust. Cepheids are young, massive stars, and young massive stars live where they were born, in the dusty spiral arms of galaxies. Dust dims starlight and reddens it, and the amount of dimming depends on how much dust is in the way, which is not known in advance. The standard solution is to observe each star at more than one wavelength, since dust affects blue light far more than red, and use the reddening to infer the dimming. It works well. It is not perfect, and there is crowding. A Cepheid in a galaxy 60 million light-years away is not a clean, isolated point. It sits in a dense field of other stars, and if your telescope cannot separate them, the brightness you measure includes light that does not belong to your star. Each of these effects is small, each is understood, each is corrected for, and each correction, if it was slightly wrong in a consistent direction across all the Cepheids in the sample, would push the final expansion rate in a consistent direction. That is the shape of the doubt that has hung over the late universe measurement for 30 years. Not that anyone made an arithmetic error, that some small, systematic, deeply buried bias in the treatment of pulsating stars might be quietly bending the entire ladder. Which raises the obvious question, and it is the question that organizes everything that follows. How do you anchor the bottom of a ladder like this to something that has nothing to do with stars at all? You anchor it with water. 23.5 million light-years from here, in the constellation of Canes Venatici, there is a spiral galaxy catalogued as Messier 106. It is a handsome object, the sort of thing amateur astronomers photograph on clear nights, with two bright spiral arms and two fainter anomalous ones that were a puzzle for years. At its center is a black hole of about 40 million solar masses, and around that black hole is a thin disk of gas, seen from here almost exactly edge-on. The gas contains water vapor. The black hole and its surrounding accretion flow flood that vapor with infrared radiation, which pumps the water molecules into an excited state. When they drop back down, they do so in a way that stimulates neighboring molecules to drop as well, and the result is a coherent amplified beam at a frequency of about 22 gigahertz. It is a laser made of water, operating in the microwave band, driven by matter falling into a black hole. The word for it is maser. There are clumps of these masers scattered around the disk, and they are bright, compact, and at a precisely known frequency, which means that with an array of radio telescopes spread across the surface of the Earth, all observing simultaneously and combining their signals, you can locate them on the sky to an angular precision of tens of micro-arcseconds. That is the technique called very long baseline interferometry, and it gives you the resolving power of a telescope the size of the planet. Here is what makes this galaxy worth so much. The maser clumps are in orbit. Their motion toward or away from us shifts their frequency by the Doppler effect, so their orbital speed can be read directly off the spectrum, in kilometers per second, with no assumptions of any kind. At the same time, watching them over years, you can see them drift across the sky, a tiny angular motion, but measurable. You can also measure their acceleration, the slow change in their frequency as they swing around the curve of the orbit. Now you have the same motion expressed in two different units, a physical speed in kilometers per second and an angular speed in micro-arcseconds per year. The ratio between a physical size and the angle it subtends is exactly what a distance is. No standard candles, no pulsating stars, no assumptions about stellar evolution, chemical composition, dust, or crowding. Newton's laws and the speed of light applied to gas orbiting a black hole. It is worth spending a moment inside that disk, because the scale of it is not obvious from the description. You are hovering somewhere above the plane of the disk, looking down. Below you is a structure, roughly a light year, across from inner edge to outer small. By galactic standards, smaller than the distance from here to the nearest star. It is warped slightly, like the brim of a hat. The gas in it is thin, and it is glowing faintly in the infrared from the radiation pouring out of the region at the center. At the middle, there is no object to see. There is a region a few hundred times the size of the solar system, inside which 40 million solar masses are concentrated, and around which everything is orbiting. The inner edge of the disk is moving at around 1100 kilometers per second. The outer edge is slower. The relationship between radius and speed follows Kepler's laws, precisely the same mathematics that describes the planets in our own system. Working unchanged around a black hole, 10 million times heavier than the Sunday. And scattered through that gas are the maser spots, each one a clump of water molecules radiating coherently at a single microwave frequency, bright enough to be picked out individually from 23 million light-years away by radio dishes on 4 continents operating in concert. Nothing about this system was arranged for our benefit. It is simply a galaxy that happens to have a maser disk, and happens to have it oriented edge-on, and happens to be close enough to resolve. We found it and used it as a meter stick. The Megamaser Cosmology Project, led by Jim Bratz and Dom Pesch at the National Radio Astronomy Observatory, spent the better part of 2 decades on this measurement. It required repeated observations across many epochs with the combined resources of the Very Long Baseline Array across the United States, the Green Bank Telescope in West Virginia, the Effelsberg Telescope in Germany, and for a period, the Arecibo dish in Puerto Rico, before its collapse in 2020. The final distance to Messier 106 is 7.576 megaparsecs, with an uncertainty of about 1.5%. 1.5% on a galaxy 23 million light-years away from pure geometry. That is the foundation stone. Because Messier 106 also contains Cepheids, and once you know the distance to the galaxy by geometry, you know the true luminosity of every Cepheid in it. The relative scale that Leavitt found becomes an absolute one. The bottom of the ladder is bolted to something that does not care about stars. There are 2 other anchors, and the modern measurement uses all 3. The second is the Large Magellanic Cloud, the same galaxy where Leavitt found her variables, now measured by a completely different route. Scattered through it are detached eclipsing binary stars, pairs of stars orbiting each other, oriented so that from our position, each one passes in front of the other once per orbit. The light curve of such a system, watched over many cycles, is enormously informative. The duration and depth of each eclipse gives the ratio of the stars' sizes. The spectra give their orbital velocities. Together, those yield the actual physical diameters of the stars in kilometers. Compare that physical size with the angular size implied by their surface brightness, and you have a distance. A team led by Grzegorz Pietrzyński, working through the Araucaria project, spent years monitoring 20 of these systems, choosing late-type giants for which the relationship between color and surface brightness is unusually well behaved. They published a distance to the Large Magellanic Cloud of 49.6 kiloparsecs, about 162,000 light-years, accurate to 1%. The third anchor is closer to home and, in principle, the cleanest of all. Parallax. Hold a finger up and close one eye, then the other, and the finger shifts against the background. The Earth's orbit gives us a baseline 300 million kilometers wide, and a nearby star observed from opposite ends of that baseline shifts fractionally against more distant stars. Measure the shift, know the baseline, and trigonometry gives the distance. It is the most direct method there is, and it works without any assumption whatsoever about what the star is or how it shines. The problem has always been that the angles are absurd. For a star 1,000 light-years away, the shift is a few thousandths of an arc-second, about the angular size of a coin in Sydney, viewed from London. The European Space Agency's Gaia satellite, launched in December 2013 and operated for over a decade from the second Lagrange point, was built to do exactly this on an industrial scale. It has measured positions for nearly 2 billion stars, with the best parallaxes precise to tens of micro-arc-seconds. Among those stars are dozens of Milky Way Cepheids, whose distances are now known by trigonometry alone. So the first rung has 3 independent geometric anchors: a maser disk around a black hole, a set of eclipsing binaries in a satellite galaxy, and direct trigonometric parallax within our own. They agree with each other. If the Cepheid calibration were badly wrong, they would not. The second rung is where Cepheids do their real work. You look for galaxies that contain both Cepheids and something else specifically. A galaxy that has, in recent decades, hosted a Type 1a supernova. These are the most useful explosions in the universe, and their usefulness comes from the specific way they happen. A white dwarf is what remains when a star like the Sun exhausts its nuclear fuel and sheds its outer layers. What is left is a core of carbon and oxygen, roughly the size of the Earth, containing roughly the mass of the Sun, held up against its own gravity, not by heat, but by a quantum mechanical effect called electron degeneracy pressure. the simple refusal of electrons to occupy the same state as one another. It is inert. It cools slowly. Left alone, it would sit there indefinitely. But if it has a companion star close enough, it can pull material off that companion and add it to itself. And degeneracy pressure has a limit. The limit was worked out by Subramanian Chandrasekhar in 1930, at the age of 19, on a steamship from Madras to England. He had won a scholarship to Cambridge and had a long voyage with nothing much to do, so he took the existing theory of white dwarfs and asked, what happens when you include special relativity because, in a sufficiently compressed star, the electrons providing the supporting pressure are moving at an appreciable fraction of the speed of light, and their behavior changes. The answer he got was that above a certain mass, degeneracy pressure fails entirely. There is no stable white dwarf heavier than about 1.4 times the mass of the sun. Anything above that has nowhere to stop. He presented the result in London in 1935. Arthur Eddington, the most eminent astrophysicist in Britain, the man who had led the eclipse expedition that confirmed Einstein's prediction of light bending, and Chandrasekhar's own mentor stood up immediately afterwards and dismissed it. He said the result was absurd, that stellar physics must contain some law preventing a star from behaving so ridiculously. He did this in front of the assembled Royal Astronomical Society, and he did it without warning. Chandrasekhar was 24. Eddington's authority was such that the field largely deferred to him, and the limit went unaccepted for years. Chandrasekhar eventually stopped defending it, moved to the University of Chicago, and worked on other things. He received the Nobel Prize in Physics in 1983, more than 50 years after the calculation. By then it was clear that what happens above the limit is not absurd at all. It is a neutron star, or a black hole, depending on how far above you go. Above that threshold, then, the electrons can no longer hold the star up. The core begins to collapse, the temperature spikes, carbon fusion ignites, and because the material is degenerate, it cannot expand to relieve the heat. The fusion runs away. In a few seconds, the entire star is consumed and unbound, and for a few weeks it shines with roughly 5 billion times the luminosity of the Sunday. The crucial point is the mass threshold. Because the explosion happens at approximately the same mass every time, it releases approximately the same energy every time. The intrinsic brightness of these events is nearly standard, which means that, like a Cepheid, how bright one appears tells you how far away it is. They are not perfectly standard. But in 1993, Mark Phillips demonstrated that the residual variation is predictable. The intrinsically brighter explosions fade more slowly. Measure the shape of the light curve, how quickly the supernova rises and declines, and you can correct for the difference. After correction, the scatter drops to a few percent, and they are visible across billions of light years, which no pulsating star is. A Cepheid becomes impossible to isolate beyond about 100 million light years. A Type 1. A supernova at that distance is trivial to observe. So, Cepheids in a galaxy give the distance to that galaxy. A supernova in the same galaxy has a measured apparent brightness. Together, they give the true luminosity of that class of explosion. That is the second rung, the handoff from stars we can resolve to explosions we can see across the observable universe. The third rung is where the answer comes out. You find Type 1, a supernovae, in galaxies far enough away that the expansion of the universe dominates their motion beyond roughly 100 million light-years, out in what is called the Hubble flow. Nearer than that, galaxies are being pulled around by their neighbors. Our own galaxy is falling toward the Virgo cluster at several hundred kilometers per second, and that local motion would contaminate the measurement. Far enough out, expansion wins. The contamination problem is worth being specific about, because it sets the minimum distance at which the measurement can be attempted at all. Every galaxy has two motions superimposed. One is the recession caused by the expansion of space, which grows with distance. The other is its own motion through space, caused by the gravitational pull of everything around it, its neighbors, its group, its cluster. Astronomers call the second one a peculiar velocity, using peculiar in its older sense of belonging to itself. Peculiar velocities are typically a few hundred kilometers per second, and they do not shrink with distance. expansion velocity does grow with distance. So the ratio of signal to contamination improves the further out you look. At the distance of the Virgo cluster, about 50 million light-years, the expansion velocity is around 1,000 kilometers per second, and peculiar motions of several hundred are a serious fraction of it. At 300 million light-years, expansion gives several thousand kilometers per second, and the same peculiar motions become a manageable few percent. Beyond that, they average out across a large enough sample. This is exactly why the ladder needs its upper rungs. You cannot measure the expansion rate nearby, where distances are easy, because local gravity drowns the signal. You have to get far enough out that expansion dominates, and at those distances, nothing except a supernova is bright enough to serve as a marker. For each of those distant supernovae, then, the calibrated luminosity gives the distance. The redshift of its host galaxy gives the recession velocity. Divide one by the other, and you have the expansion rate. That is the whole architecture. Geometry to Cepheids, Cepheids to supernovae, supernovae to the expanding universe. 3 rungs, each independently checkable, each with its own error budget. The first serious attempt to walk it end-to-end with a real space telescope was the Hubble Space Telescope Key project, one of the 3 flagship programs the telescope had been built for. It ran through the 1990s, led in its later years by Wendy Friedman of the Carnegie Observatories in Pasadena. Her team found Cepheids in galaxies out to about 80 million light-years, calibrated the supernovae, and in 2001 announced a result: 72 kilometers per second per megaparsec, plus or minus 8, an 11% uncertainty. For the time, that was a triumph. When the Key project began, published values for the expansion rate ranged from about 50 to about 100, and the 2 camps arguing for the extremes had been doing so, with considerable heat, for 30 years. The disagreement was so entrenched that some astronomers had stopped quoting a value at all and simply carried the uncertainty through their calculations as an unknown factor. The Key project collapsed that range into a single number with an error bar you could work with. An 11% uncertainty is also large enough to hide almost anything. The early universe measurements available at the time had uncertainties of their own of several percent. The 2 overlapped comfortably. There was no tension. There could not be. Neither side was sharp enough to have one. And then, within a decade, both sides got very much sharper. Adam Riess did not set out to break cosmology. He had already helped rearrange it once, and that had been quite enough. In 1998, as a young researcher at Berkeley, he was the lead author on a paper from the High Z supernova search team. The team had been measuring distant Type 1a supernovae in order to determine how much the expansion of the universe was slowing down. That was the expected result. Gravity attracts. A universe full of matter should decelerate. The only question was by how much, and whether the deceleration was severe enough that everything would eventually fall back together. The supernovae came out fainter than expected. Not dramatically, around 25% fainter than they should have been at their measured redshifts. But fainter means further away than the model predicted, which means the universe had expanded more in the intervening time than a decelerating universe could account for. Riess has described spending weeks trying to find the error, and the description is worth taking at face value rather than as modesty. A result showing that the universe is accelerating had, at that point, no theoretical constituency. It required reintroducing a term into Einstein's equations that Einstein had put in for a different reason, removed, and reportedly regretted. Nobody's model wanted it. The professional expectation for a young researcher producing that result was that they had made a photometry error or mishandled dust. He wrote in a note to his collaborators at the time, in effect, that the data required something none of them believed, and that they had better be very sure before saying so. A competing group at Berkeley, the Supernova Cosmology Project, led by Saul Perlmutter, arrived independently at the same conclusion within months. The expansion is not slowing. It has been accelerating for roughly the last 5 billion years, driven by something that behaves like an energy inherent to empty space itself. Riess, Brian Schmidt, and Perlmutter shared the Nobel Prize in Physics in 2011 for that result. We have been calling the cause dark energy for a quarter of a century, and the name has not become any more informative in that time. It accounts for roughly 70% of the total energy content of the universe, and the honest state of knowledge about what it is remains close to zero. After that, Rius turned his attention to a quantity that had begun to matter more than it used to. Once you accept a universe containing dark energy, dark matter, and ordinary matter, the whole picture becomes tightly interlocked. The expansion rate today is not an isolated fact. It constrains the dark energy density. It constrains the age. It feeds back into the interpretation of the microwave background. Measuring it precisely was no longer a matter of tidying up an old argument. It had become a test of whether the interlocking picture held together. The tool that made a serious attempt possible arrived in May 2009 aboard the final Space Shuttle mission to service the Hubble Space Telescope. Wide Field Camera 3 was installed by astronauts during a spacewalk, replacing an instrument that had been in orbit for 16 years. Its advantage for this particular problem was that it observed well into the near-infrared. Infrared matters enormously for Cepheids, for two reasons. Dust scatters short wavelengths far more efficiently than long ones, so observing in the infrared cuts the dust problem down by a large factor. And the period luminosity relation itself is tighter at infrared wavelengths, with less intrinsic scatter and a weaker dependence on chemical composition. Everything that had made the Cepheid rung uncomfortable became less uncomfortable in the infrared. Rius assembled a program around it, called SHOES, the letters standing for supernova, H0 for the equation of state, where H0 is the symbol physicists use for the present-day expansion rate. The goal was straightforward: bring the uncertainty down from the key project's 11% to a few percent, and then keep going. His expectation, stated repeatedly at the time, was that the number would settle somewhere near the value emerging from the microwave background. The Wilkinson probe had suggested around 70. The key project had given 72 plus or minus 8. There was no reason to anticipate a fight. The two methods were expected to converge, the way independent measurements of the same quantity normally do, and the convergence itself would be a nice confirmation that the standard model was sound. In 2011, SHOES published its first major result. Using the new camera, the team had measured Cepheids in 8 galaxies that had hosted well-observed Type 1a supernovae. The list included the supernova of 1994 in a galaxy in Virgo, and one that had gone off in the Pinwheel Galaxy in 2011, close enough that amateur astronomers photographed it from back gardens. They anchored the Cepheid scale on the Mazar distance to Messier, 106, and on the Large Magellanic Cloud. The answer was 73.8 kilometers per second per megaparsec, plus or minus 2.4. 73.8. Not 70. Not 72. Rius has been consistent about his reaction, and it was not excitement. He thought his team had made a mistake. They went back through the analysis. They tested every systematic they could name. They changed the way the Cepheids were selected, changed the treatment of dust, changed the anchors, removed galaxies from the sample one at a time to see whether any single object was driving the result. The number did not move. 2 years later, in March 2013, the Planck collaboration released its first cosmology results, 67.3, plus or minus 1.2. At a conference that year, the two numbers were put side by side. George Efstathiou, the Cambridge cosmologist who had led much of the Planck analysis, stood up and made an observation that a room full of physicists had not expected to hear. He said, in effect, that if Rius was right, then the standard model of cosmology had a problem. It was not delivered as an attack, and it should not be read as one. It was a conditional statement of an obvious logical fact. Two precise measurements of the same physical quantity cannot disagree unless one of them contains an unidentified error, or the framework connecting them is missing something. At the time, the gap stood at about 2.5 standard deviations. In physics, that is a shrug. 2.5 sigma anomalies appear constantly, and the overwhelming majority of them evaporate when the data improves. Everyone in the room had seen a dozen of them come and go. The reasonable expectation was that this one would do the same. It is worth understanding the mood of the field going into this, because it explains why the response was so slow. The standard model of cosmology, lambda cold dark matter, named for the Greek letter Einstein used for the cosmological constant and for the cold, slow-moving dark matter that dominates the mass budget, had spent 2 decades being right about things it had no business being right about. It predicted the acoustic peaks in the microwave background before anyone measured them, including their spacing and relative heights. It predicted the pattern of galaxy clustering that later surveys found. It absorbed the discovery of accelerating expansion by adding one parameter and carried on working. 6 numbers, fitted once, reproducing the structure of the universe across 14 billion years and a factor of 1,000,000 in scale. Cosmology had, as a result, become a science of refinement. The parameters were approximately known. The job was to sharpen them. Under those conditions, the professional expectation attached to any new measurement is agreement, and disagreement reads as an error not yet found. So the sharpening continued from both directions. And this is where the story stops behaving normally. By 2015, Planck's second release had tightened the early universe number to 67.8 plus or minus 0.9. Schütz had incorporated the first Gaia parallaxes and more supernova hosts and published 73.2 plus or minus 1.7. The gap was now 3.4 sigma. Sigma is worth defining properly since the entire escalation of this story is measured in it. It is a statement about how far apart 2 results are, expressed in units of their own combined uncertainty. If 2 measurements differ by exactly the size of their error bars, that is 1 sigma, and the odds of chance alone producing that much separation are about 1 in 3, perfectly ordinary. 2 sigma is about 1 in 22. 3 sigma is roughly 1 in 370. Particle physicists conventionally do not take an anomaly seriously below 3 sigma, because at that level, given how many measurements are made every year across the field, you would expect several apparent effects to be pure noise. 5 sigma, the discovery threshold, is another 2 steps beyond that, and each step is far larger than the one before it. The scale is not linear, but exponential. So 3.4 sigma means the odds of a fluke are worse than 1 in 1,000. That was the point at which the language changed. In conference talks and in papers, people stopped using the word discrepancy and began using the word tension. It sounds like a small thing. It was not. A discrepancy is a puzzle sitting on a desk. A tension is a structural condition, a load the building is carrying. Theorists began publishing. The first proposals for new physics that could accommodate both numbers appeared on the preprint servers, tentatively at first, then in a steady stream. By 2018, the Planck final release gave 67.4, plus or minus 0.5, and Schütz, with more hosts and better parallaxes, reached 73.5, plus or minus 1.6, 4.4 sigma. Odds of a fluke, worse than 1 in 100,000. It is worth pausing on what those error bars mean physically, because the numbers pass by quickly. Plus or minus 0.5 kilometers per second per megaparsec means that the Planck team was claiming to know the expansion rate of the entire universe to better than 1 part in 130. A megaparsec is 3.26 million light-years. They were saying that across that distance, the recession velocity is known to within half a kilometer per second, about the speed of a brisk walk. And Schütz was making a comparably confident claim from an entirely unrelated direction, and the 2 claims were incompatible. By 2019, with the Schütz team's improved treatment of the Large Magellanic Cloud anchor, the local number came in slightly higher still, near 74, and the combined significance crossed 5 sigma. There was no announcement. Nobody held a press conference. 5 sigma in particle physics arrives at a specific experiment on a specific day and gets champagne. Here it arrived through the accumulated weight of a dozen analyses, several review papers and a long series of conference sessions, and the appropriate reaction was not celebration, but a kind of institutional unease. Because a 5 sigma result is, by the field's own standard, a discovery. And this discovery consisted of the statement that the 2 most precisely measured quantities in cosmology do not fit together. What is striking, reading back through that decade, is how reluctant everyone involved was. Rias has spoken about the internal progression from "we must have missed something" to "we cannot find anything we missed," to the possibility that the problem is not in the measurement at all. That is not the arc of someone who wanted to overturn a model. It is the arc of someone who kept trying to close a gap and could not. His team published incrementally, tested exhaustively, and waited for independent confirmation before raising their voices. The professional risk of being the person who declared the standard model broken and then turning out to have a subtle photometry error is not small. Careers in cosmology are built on being right. Eustathiou carried the equivalent weight from the other side. For years, he was the most prominent voice, arguing that the Planck result might be missing something, precisely because he was the person best placed to know what could be missing. He said publicly that the tension was the most interesting problem in cosmology, and that if it was real, it would require an extension to the standard model. He also said, consistently, that his team had examined their error budget with everything they had, and could not find a systematic capable of moving their number far enough. Neither man was being dogmatic. Both were doing the thing that is actually difficult, which is to report a number accurately and then say, out loud, that you do not know what it means. Meanwhile, a specific worry was hardening into the leading explanation for how the local number could be too high, and it had nothing to do with arithmetic. Cepheids live in crowded places. They are young, massive, short-lived stars, which means they are found in the dusty, star-forming regions of spiral disks, surrounded by other young stars. The Hubble Space Telescope has a 2.4-meter mirror and sits 550 kilometers above the ground. Its resolution is superb by any historical standard. It is not infinite. In a galaxy 50 or 60 million light-years away, the region of a spiral arm that falls within a single resolution element of wide-field camera. 3 is not one star. It is a crowd. If a Cepheid has unresolved neighbors contributing light to the same pixels, the measured brightness is too high. A star that appears too bright is inferred to be too close. Distances come out too small. And an expansion rate is a velocity divided by a distance. So distances that are systematically too small give an expansion rate that is systematically too large. The SHOES team knew this from the beginning. They corrected for it, using artificial star tests, injecting fake stars of known brightness into the real images, and measuring how much the surrounding crowd distorted the recovered photometry, and using statistical subtraction of the background, stellar population. But a correction is a model. And the critics could always ask, entirely reasonably, what if the correction is not quite complete? What if a small residual bias, in the same direction for every Cepheid in every host galaxy, is quietly inflating the entire ladder by a few percent? A few percent is all it would take. There was only one way to answer it. Look at the same stars with a telescope sharp enough that the crowd resolves into individuals. That telescope was, at that moment, still being assembled in a clean room. Wendy Friedman did not have to come back to this. She had already led the project that gave the field its first trustworthy answer. The key project had run for a decade, involved dozens of people, consumed a substantial fraction of the Hubble Space Telescope's early observing time, and ended a 30-year argument. She had become director of the Carnegie Observatories in Pasadena, responsible for the institution's telescopes in Chile, and for the early development of what would become the giant Magellan telescope. There was no professional obligation to revisit the Hubble constant, and considerable reason not to. The reason she did is worth stating precisely, because it is not the reason a spectator would assume. It was not a wish to prove Rees wrong. It was that the Cepheid distance scale was hers. She had spent a career building confidence in it, and she was among the small number of people who knew exactly where its soft spots were: the metallicity correction, the dust treatment, the crowding, the assumption that a relation calibrated in one galaxy transfers cleanly to another. If any of those was subtly biased, the consequences would not stop at the expansion rate. The same Cepheid calibration feeds into supernova luminosities, which feed into the dark energy measurements, which feed into essentially the whole late-time cosmological picture. So she decided to build a second ladder, not a refinement of the first, a separate one, sharing as little with it as possible. The idea she reached for had been sitting available for decades, and it involves a moment in the life of a star that lasts a few minutes and can be seen across 60 million light-years. Consider a star somewhat less massive than the Sun, old, having exhausted the hydrogen in its core. It has moved off the main sequence and become a red giant. Hydrogen is now fusing in a thin shell around an inert core of helium, and the ash from that shell is falling onto the core, which grows steadily heavier. The core is not fusing. It is held up by the same electron degeneracy pressure that holds up a white dwarf. It contracts and heats and contracts further and heats further, and the star's outer envelope swells enormously in response, cooling and reddening as it expands. This continues until the core temperature reaches about 100 million degrees. At that point, helium ignites, and because the core is degenerate, it cannot do what a normal gas would do, which is expand and cool and moderate the reaction. The pressure in a degenerate gas barely depends on temperature. So the fusion heats the core, which does not expand, which makes the fusion faster, which heats it further. The reaction runs away in a thermal runaway that releases, for a few seconds, an energy output comparable to that of an entire galaxy, every bit of it absorbed internally, lifting the degeneracy, none of it visible from outside. It is called the helium flash, and when it is over, the star has been restructured. It settles onto a different, fainter configuration, and continues its life elsewhere on the diagram. Here is what makes it useful. The core mass required to trigger the flash is set by fundamental physics by degeneracy and the nuclear reaction rates, and it is very nearly the same for every low-mass star, regardless of the star's total mass, its age, or the details of its history. The same core mass means the same luminosity at the moment of ignition. So if you take a galaxy, photograph it deeply, identify tens of thousands of individual stars, and plot each one's brightness against its color, the red giants trace a clear sequence rising toward brighter magnitudes. And, at a particular brightness, that sequence stops, abruptly. There are red giants below the cutoff, and essentially none above it, because any star that got that bright underwent the flash and left. That edge is the tip of the red giant branch. It is a knife edge in a statistical distribution of thousands of stars, and it corresponds to a known absolute luminosity. It is worth looking at one of these diagrams, because the effect is not subtle and the way it appears is unlike anything else in observational astronomy. Picture a plot. Along the bottom, color bluer stars on the left, redder on the right. Up the side, brightness, with the brightest at the top. Every star measured in the outskirts of some distant galaxy becomes one dot. At first, it looks like scatter. Thousands of points, a smear. Then structure emerges. There is a broad diagonal band running up and to the right, getting brighter as it gets redder. That is the red giant branch stars at various stages of the same process, arranged along it by how far through that process they have traveled. Follow the band upward. It thins, as bands do, because there are fewer stars in the brief late stages than in the long early ones. And then it stops. Not fades. Stops. There is a horizontal line above which the density of points collapses to almost nothing, and it is sharp enough to see by eye once you know to look for it. Above that line, stars have undergone the helium flash and moved elsewhere on the diagram. Below it, they have not yet. The measurement consists of finding the vertical position of that line in a plot of thousands of dots as precisely as possible. It is not a measurement of any individual star. It is a measurement of where a population ends. Its advantages over Cepheids are specific, and they are not small. Red giants are old stars. Old stars have had billions of years to migrate out of the disks where they formed and into the extended halos of their galaxies. So you look for them out in the sparse outskirts, away from the spiral arms, which means far less crowding and far less dust, because there is little dust in a galactic halo. You do not need to time anything. A Cepheid requires monitoring across many epochs to establish its period. The red giant tip requires a single deep image because the measurement is not about a star's behavior but about where a population's brightness distribution terminates. And the tip's dependence on chemical composition, while real, is weaker in the near-infrared than the equivalent Cepheid dependence, and can be handled by restricting the measurement to the metal-poor halo population. There are costs. Identifying an edge in a luminosity function requires large numbers of stars and careful statistical treatment, and the exact location of the edge depends on the algorithm used to find it. The absolute calibration still has to come from somewhere, from the Large Magellanic Cloud and from the Mesa galaxy, the same anchors the Cepheid ladder uses. And red giants are intrinsically fainter than Cepheids, which limits how far out the method reaches. The method was not new. Astronomers had recognized the red giant tip as a potential distance indicator since the 1950s, and Barry Madore and Friedman herself had worked on the theory of it decades before it became relevant to this argument. What had been missing was not the idea but the photometry. You cannot find an edge in a luminosity function unless you can measure thousands of individual faint stars in a distant galaxy's halo cleanly, and until space telescopes with infrared detectors existed, you could not. Madore is worth mentioning for a reason beyond collaboration. He and Friedman have worked together for more than 40 years on the key project and on everything since, and much of the theoretical groundwork for treating both Cepheids and red giants as calibratable standard candles came out of that partnership. When the Carnegie-Chicago program argues that the red giant tip is less prone to systematic error than the Cepheid scale, it is not an outsider's criticism of somebody else's method. It is two people who built a great deal of the Cepheid scale, saying that they think the other approach is cleaner. Friedman launched the Carnegie-Chicago Hubble program to do it properly. Her longtime collaborator and husband, Barry Madore, worked on it with her, along with a group of postdoctoral researchers and students. They used the Hubble Space Telescope to image the halos of galaxies that had hosted Type 1, a supernovae, found the red giant tip in each, and built a distance ladder with the same three-rung architecture, but a different first rung. Geometry to red giants to supernovae, supernovae to the Hubble flow. In 2019, they published 69.8 kilometers per second per megaparsec. It sat between the two camps, about 2 sigma below the local Cepheid value, about 2 sigma above the Planck value, in tension with both, comfortable with neither. The immediate temptation is to read that as a resolution, a third measurement landing in the middle, suggesting the truth is somewhere in between and both sides have modest errors. That reading is wrong, and it is worth being clear about why. A middle value only resolves things if it is consistent with both extremes. This one was not. Its error bars excluded both. A measurement that disagrees with everybody has not split the difference. It has added a third position to a two-way disagreement. And a third position carries a specific implication that a simple middle value would not. If there were only two numbers, the space of explanations is manageable. Either the early measurement is off, or the late one is, or the model connecting them is incomplete. 3 plausible stories, with 3 numbers, all measured carefully, all disagreeing with each other. The story has to accommodate more. Now you need an account in which the microwave background reads low, the Cepheid ladder reads high, and a red giant measurement of the same host galaxies reads somewhere between the two. If the answer was simply that Cepheid crowding inflates the local number, the red giant tip should have landed on Planck, because it does not suffer from crowding. It did not land on Planck. So whatever is happening, it is not the single clean systematic that everyone had been hoping to find. What happened next has nothing to do with numbers, and it is the part of this story that has aged best. Adam Riess and Wendy Friedman are not enemies. They have known each other for decades. Friedman was a senior figure when Riess was young in the field. He has praised her work publicly and repeatedly. They agree about the great majority of the underlying physics. They disagree about which rung is more trustworthy, and they have disagreed in public, in print, with data, for years. Riess's position is that the Cepheid calibration is now the most thoroughly interrogated distance scale in astronomy. Anchored 3 separate ways, verified with the sharpest instrument ever built, and that the red giant tip carries calibration uncertainties, particularly in its absolute 0 point and its sensitivity to the stellar populations sampled that are not yet as well characterized as its advocates suggest. Friedman's position is that the Cepheid method's residual crowding and metallicity corrections, however carefully modeled, remain corrections applied to a systematically difficult measurement, and that a method requiring no corrections of that kind should be preferred even at the cost of some statistical precision. Both of those are defensible. Neither is a fudge. and each is being argued by someone who has spent their working life on exactly the question at issue. The technical core of the disagreement, for anyone who wants it, is narrower than the summary suggests. The red giant tip's absolute brightness has to come from somewhere. Friedman's team calibrates it primarily using the Large Magellanic Cloud, where the eclipsing binary distance is known to 1%, and cross-checks against the Mesa galaxy. Ries's group has argued that the tip brightness measured in the Large Magellanic Cloud's halo may not transfer cleanly to the halos of the more distant, more massive host galaxies, because the stellar populations there are not identical, different average ages, different chemical compositions, different mixes of stars near the tip. There is also a question of exactly how you locate the edge. Because a real luminosity function does not have an infinitely sharp cut-off, photometric errors and population effects blur it, the tip position is extracted with an edge detection algorithm, and different reasonable choices of algorithm and smoothing can shift the answer by a few hundredths of a magnitude. A few hundredths of a magnitude, propagated through the ladder, is worth roughly a unit in the final expansion rate. That is the whole substance of it, not a clash of worldviews, a disagreement about the transferability of a calibration and the treatment of an edge in a histogram, with about 4 units of the Hubble constant riding on the outcome. It is also worth noting where this is happening. Friedman works at the Carnegie Observatories, the institution founded by George Ellery Hale, whose telescope on Mount Wilson is the one Hubble used to find the Cepheid in Andromeda and to derive the redshift distance relation. The argument about the expansion rate has, in a fairly direct institutional sense, been running in the same building for a century. In 2019, the two presented back-to-back at a meeting in California. Neither declared victory. Neither described the other's work as invalid. What the audience was watching was a genuine scientific standoff at the precise boundary of what the available instruments could decide the rarest and most useful thing a field can have, because it means the disagreement is about evidence rather than about temperament. That kind of standoff has an obvious resolution condition. You need a better instrument. One was, by then, being fueled. The James Webb Space Telescope launched on Christmas Day, 2021, from Kourou in French Guiana. It reached the second Lagrange point a month later, unfolded over the following weeks, in a sequence involving 344 single-point failures, any one of which would have ended the mission, and began science operations in July 2022. Both teams had programs approved. Ries held director's discretionary time, observing hours held back from the normal proposal cycle for questions considered too urgent to wait to re-observe his Cepheid host galaxies with the new instrument and test. For crowding bias directly, Friedman's team had a parallel program to measure the red giant tip in overlapping targets with the same telescope, at the same resolution, in the same filters. For the first time, the two ladders would be measured with a single instrument, removing at a stroke every argument about differences between telescopes. The expectation, on both sides and in the wider field, was that this would settle it. Either the Cepheids would shift downward when the crowding was resolved away, vindicating the low camp, or they would not, and the distance ladder would have survived its most serious challenge. What actually arrived was neither, and it took a while for anyone to say so plainly. While those two ladders were being argued over, other people were building things that were not ladders at all. This matters more than it might appear. The entire case for doubting the local measurement rested on the idea that something in the treatment of stars was biased. Cepheids and red giants are both stars, both calibrated against overlapping anchors, both subject in principle to related worries about crowding and composition. A skeptic could reasonably argue that the two methods, for all their differences, were not independent enough to check each other properly. So the interesting question became whether the expansion rate could be measured without stars. The Megamesa measurement was the first to deliver, and it is the cleanest thing in this entire story. We have already met the disk of water vapor orbiting the black hole at the center of Messier 106, and the use of that geometry to anchor the bottom of the distance ladder. But the same technique can be applied directly to galaxies far enough away that their motion is dominated by cosmic expansion, and when it is, no ladder is required at all. You measure the geometric distance to a distant galaxy from the orbital mechanics of its Mesa disk. You measure its recession velocity from its redshift, and you divide. There are not many suitable systems. The disk has to be nearly edge-on, the masers have to be bright enough to detect, and the galaxy has to be far enough out to sit in the Hubble flow. The Mega Maser Cosmology project spent 2 decades finding 6 of them. Bratz and Pesch and their collaborators published the combined result in 2020. 73.9 kilometers per second per megaparsec, plus or minus 3. Its precision is not competitive with the Cepheid ladder. Its independence is total. No standard candles, no stellar physics, beyond the assumption that gas orbiting a black hole obeys Newtonian mechanics. No calibration inherited from anyone else. If the entire stellar distance scale were biased upward by 7%, this measurement would have exposed it. It did not. It landed on the high side, next to the Cepheids. The second stars-free method uses gravity as a lens and time as a ruler. When a very massive galaxy sits almost exactly on the line of sight to a distant quasar, a supermassive black hole, feeding voraciously and outshining its entire host galaxy, the gravity of the foreground galaxy bends the quasar's light around it. Instead of one image, we see 2 or 4 arranged around the lensing galaxy. Occasionally, the alignment is close enough to produce a ring. The light forming each of those images took a different path to get here. The paths have different lengths, and they pass through different depths of the gravitational well, which also delays them by a different amount. So the images are not showing us the quasar at the same moment. One is showing us slightly older light than another. Quasars flicker. Their brightness varies erratically as material falls inward, on timescales of days to months. So if you monitor all the images of a lensed quasar and watch the same flicker pattern appear in each, you can measure the delay between them directly: a few days, a few weeks, sometimes over a year. That delay is a physical length divided by the speed of light, and how long the paths are depends on the overall distance scale of the universe, which means the time delay is sensitive to the expansion rate directly, with no distance ladder underneath it at all. The difficulty is entirely in the lens model. To convert a measured delay into a distance, you have to know how the mass of the foreground galaxy is distributed, including its dark matter, and you have to account for every other mass along the line of sight. There is a known and genuinely nasty ambiguity in this, called the mass sheet degeneracy. A family of different mass distributions can produce identical image positions and identical delays while implying different distances. Breaking it requires additional information, usually the measured motions of stars inside the lensing galaxy. The Holikow collaboration and its successor project took this on for 6 systems. Sherry Suyu, now at the Max Planck Institute for Astrophysics and the Technical University of Munich, has been among its leaders. The work is slow. A single system takes years of monitoring plus enormously detailed modeling. Their headline result was 73.3, plus or minus 1.8. High again. When the team later reanalyzed the systems with far more conservative assumptions about the lens mass profiles, deliberately loosening the profiles, constraints to see how much the answer depended on them, the central value stayed near 74, while the error bars ballooned to several units. So the measurement is not as sharp as the headline number implies, and the team has been candid about that. But it does not move downward when you relax the assumptions. It just becomes less certain. The third method arrived by accident, in the space of about 2 minutes. On the 17th of August, 2017, the detectors of the Laser Interferometer Gravitational Wave Observatory in Hanford, Washington, and Livingston, Louisiana, together with the Virgo detector near Pisa, registered a signal lasting about 100 seconds and sweeping upward in frequency. It was the sound, if the word can be stretched, of 2 neutron stars spiraling into each other and merging, about 130 million light-years away. Less than 2 seconds after the merger, gamma-ray satellites in orbit detected a short burst from the same region of sky. Within 11 hours, telescopes across the southern hemisphere had located a new point of light in a galaxy in the constellation Hydra, a kilonova. The glow of a few Earth masses of freshly forged heavy elements, including a quantity of gold and platinum measured in planetary masses, expanding and cooling. Roughly 70 observatories eventually followed it, in every band from radio to gamma ray. For the purposes of tonight, One specific property of that event matters. A gravitational wave signal carries its own distance information, and it does so in a way that nothing electromagnetic can. The amplitude of the wave, the actual physical amount by which space is stretched and squeezed as it passes, depends on the masses of the objects, their orbital geometry, and how far away they are. The masses and the geometry are encoded in the shape of the signal itself, in the way its frequency and amplitude evolve. So, the distance falls out of general relativity directly, with no calibration and no reference to any other astronomical object. That is why these events are called standard sirens. By deliberate analogy with standard candles, a candle has to be calibrated against something. A siren calibrates itself. Pair that self-calibrated distance with the redshift of the host galaxy, which the optical counterpart made it possible to identify, and you have an expansion rate that touches neither the microwave background nor the distance ladder at any point. There is a second reason that event is worth knowing about, which has nothing to do with expansion rates and everything to do with what the material around you is made of. Stars manufacture elements up to iron. Beyond iron, fusion stops releasing energy and starts consuming it. So the heavier elements have to be built another way, by nuclei absorbing free neutrons faster than they can decay, and then decaying into stable, heavier species afterwards. That process requires an environment absurdly rich in free neutrons, and for decades the leading candidate was the interior of a supernova, with the theory never quite working. Two colliding neutron stars are, by a considerable margin, the most neutron-rich environment in the universe. When they merge, a fraction of a solar mass of that material is flung out, and in the seconds after ejection it builds heavy nuclei at an enormous rate, then glows for days from the radioactive decay of what it has made. The spectra of that glow, followed by telescopes across the southern hemisphere, matched the prediction. The event manufactured heavy elements in quantities that are hard to state without sounding like exaggeration, including gold and platinum measured not in tons but in multiples of the mass of the Earth, which resolves an old question about where the gold in a wedding ring comes from. It was made in the collision of two dead stars sometime before the Sun formed, and then sat in a molecular cloud for a few billion years, waiting to be incorporated into a planet. That is a genuine result, and it arrived as a side effect of an instrument built to test general relativity. For the expansion rate, the result was about 70 kilometers per second per megaparsec, with an uncertainty of roughly 15%. 15% is far too broad to arbitrate anything. The measurement is consistent with Planck, with shoes, and with the red giant value simultaneously. From a single event, that is all it could be. The reason it is so broad is worth understanding, because it is the main obstacle to the method, and it is not going to be solved by building better detectors alone. A gravitational wave source that is far away and oriented face-on produces almost the same signal amplitude as one that is nearer and tilted. Distance and inclination are tangled together in the measurement, and the tangle cannot be undone from the wave alone. For this particular event, the tangle was partly broken, because the jet that produced the gamma-ray burst could be studied by radio telescopes over the following months, and its structure constrained the viewing angle. Most future events will not come with that bonus. Its importance is not the number. It is that the method works, and that the method has no shared assumptions with anything else in this story. Enough events with identified host galaxies, and the uncertainty falls roughly as the square root of the number of detections. A few dozen would bring it to a few percent. At that point, the argument acquires a referee that neither side has any prior claim on. There have been other approaches, less prominent but pointing the same way. Surface brightness fluctuations using the statistical graininess of an elliptical galaxy's light, which arises because more distant galaxies have more stars per resolution element and therefore look smoother, give a value in the low 70s. The Tully-Fisher relation, connecting a spiral galaxy's rotation speed to its luminosity, gives a similar range. Neither is as precise as the leading methods. Neither lands in the high 60s. Step back and look at the whole landscape, and the shape of it is unmistakable. On the early universe side, the Planck satellite, the Atacama Cosmology Telescope, the South Pole Telescope, 3 instruments, 2 of them ground-based, on 3 continents, with different detectors and different teams. all clustering between 67 and 69, all of them measuring the microwave background, all of them, crucially, deriving the expansion rate through the same calculated ruler. On the late universe side, the Cepheid ladder at 73, the megamasers at 74, the lensed quasars at 73, the red giant tip a shade under 70, the single gravitational wave event at 70, with wide bars. Different objects, different physics, different wavelengths, different calibrations, different failure modes. Not one method that measures the local expansion directly comes back in the high 60s. Before that observation is allowed to carry too much weight, one qualification has to be entered honestly, because it is the strongest argument the other side has. The word independent is doing heavy lifting in the paragraph above, and it is not equally true of every entry on the list. The Cepheid ladder and the red giant ladder differ in their first rung and share everything after it. Both hand off to Type 1a supernovae, and both use overlapping sets of anchor galaxies if there were a problem with how supernova luminosities are standardized if, for instance, the calibrating supernovae in nearby galaxies were systematically slightly different from the distant ones out in the Hubble flow. Because of the age or metal content of their host environments, that error would propagate into both ladders identically. Neither would flag it. This is not a hypothetical concern. It is an active area of investigation. Type 1. A supernovae in older, more massive host galaxies do appear to be slightly brighter after standardization than those in younger hosts, and the correction for that effect is applied, but not universally agreed on. The megamasers and the lensed quasars genuinely do not share this. Neither touches a supernova, and they are also the two least precise entries on the high side. So the fair statement is not that every local method is independent and they all agree. It is that the two methods, with no shared rungs at all, are the least precise ones, and they land high, and that the precise ones share a rung whose systematics are understood but not perfectly. That is a weaker claim than the enthusiastic version, and it is the one the evidence actually supports. The probability that every one of these is independently biased upward by roughly the amount required to fake the disagreement is not zero. Science does not deal in zeros, but the list of things that would all have to be wrong in the same direction by the same amount, for unrelated reasons, has grown long enough to be uncomfortable, which shifts the weight of the question in a specific way that is worth stating carefully. For most of the 2010s, the working assumption was that somebody had made a mistake, and the job was to find it. That framing put the burden on the local measurement, because the local measurement involves messier astrophysics and more corrections. The accumulation of independent local results does not prove the local number correct. What it does is remove the easy explanations one at a time. It is no longer sufficient to point at Cepheid crowding, because the masers have no Cepheids. It is no longer sufficient to point at supernova standardization, because the lensed quasars have no supernovae. Each independent method that lands high converts a plausible local error into a less plausible one. And that leaves the other end of the chain looking increasingly exposed. Because the early universe number, for all its extraordinary internal consistency, is the one that is not a direct measurement. It is an inference through a ruler that is computed rather than observed. If everything local is right, then something about the computation is not. But one local systematic was still standing, and it was the biggest one. The crowding worry had never actually been tested. It had only been modeled. The telescope built to test it had been at work for a year. The mirror is 6.5 meters across, and it is made of beryllium. Beryllium is an unusual choice and a deliberate one. It is stiff, it is light, and most importantly, for an instrument that must operate at 40 degrees above absolute zero, it barely changes shape as it cools. A glass mirror of that size would distort by an unacceptable amount on the way down to operating temperature. The 18 hexagonal segments were machined, polished at room temperature, cooled to cryogenic temperature to see how they deformed, then polished again to compensate for that deformation, so that they would arrive at the correct figure only once they were cold and in space. Each segment was then coated with about 100 nanometers of gold, chosen because gold is an excellent reflector in the infrared. The whole assembly was too large to fit inside any rocket. which meant the mirror had to fold. So did the sunshield, 5 separate layers of a polymer film, each about the thickness of a human hair or less, deployed to the area of a tennis court, whose job is to keep the sun's heat off the optics well enough that the observatory can radiate itself down to cryogenic temperature without any refrigeration for most of its instruments. The temperature difference across those 5 layers is over 250 degrees. It launched on the 25th of December, 2021, on an Ariane 5 from Kourou in French Guiana, and spent the following month unfolding on the way to the second Lagrange point, the same position where the Planck satellite had mapped the microwave background a decade earlier. 2 instruments, in the same gravitational parking space, measuring the same quantity from opposite ends of cosmic history. The unfolding sequence involved around 344 single-point failures mechanisms with no backup, any one of which could have ended the mission with no possibility of repair, because unlike its predecessor, this telescope is 1.5 million kilometers away and no astronaut is going out there. None of them failed. For the specific problem in front of us, only one property of this telescope matters, and it is resolution. The Hubble Space Telescope has a 2.4-meter mirror. Webb has 6.5. The resolving power of a telescope at a given wavelength scales with the diameter of its aperture, which means Webb is roughly 2.5 to 3 times sharper in the near-infrared than its predecessor at the same wavelengths. In imaging terms, that is not a marginal gain. The area of sky contained in a single resolution element shrinks by roughly a factor of 7 or 8. Apply that to a crowded spiral arm in a galaxy 50 million light-years away, and the crowd starts resolving into individuals. A patch that Hubble recorded as one blended smear becomes, in Webb's near-infrared camera, a Cepheid with its neighbors sitting on separate pixels around it, each with its own measurable brightness. It is worth being concrete about what the difference looks like. Take one Cepheid in the Pinwheel Galaxy. In the Hubble images, it is a small, bright blob, a handful of pixels across, sitting in a background that is not black, but a faint mottled glow, the unresolved light of thousands of stars too close together to separate. The blob has a brightness, and the brightness is measured by summing the light in a small aperture and subtracting an estimate of that background. The estimate is the problem. Some of what you are subtracting is genuinely background. Some of it is a star sitting almost exactly behind your target. Now take the same field in the Webb images. The mottled glow has broken up. Where there was a smooth, faint haze, there are now individual points, dozens of them, within the area the old aperture covered. Your Cepheid is one of them, distinctly separated from its neighbors. And the light you are attributing to it is actually its own. You do not need statistics to see that this is a better measurement. You can see it by putting the 2 images side by side, which is precisely what made the test decisive, and precisely why the result was not what most people expected. That is the whole test. Take the same stars. Look again with an instrument that cannot be fooled by blending in the way the old one might have been. See whether the brightnesses change. Ries secured director's discretionary time in the telescope's first observing cycle. The target list was the backbone of the Shoes ladder. Messier 106, where the Mazaranka lives. The Pinwheel Galaxy, host of the 2011 supernova, and several other supernova hosts, covering a range of distances so that any crowding bias, which should worsen with distance as the resolution element covers more physical area, would show up as a trend. The observations were carried out across 2022 and 2023. The team then did something methodologically important. Rather than starting fresh, they ran the identical analysis pipeline they had used on the Hubble data. Same photometry procedures, same period luminosity fitting, same treatment of dust and metallicity, same distance calculations. The only thing that changed was the telescope. Then they compared, star by star, galaxy by galaxy. You can picture the scene without much effort, a scatter plot on a screen. One axis is the brightness of each Cepheid as measured by Hubble. The other is the brightness of the same Cepheid as measured by Webb. If the crowding worry is correct, the points should scatter systematically off the diagonal, with the Hubble measurements too bright, and increasingly so for the more distant galaxies. It is worth registering how few objects this comes down to. The entire local measurement of the expansion rate of the universe rests on Cepheids in something like 40 galaxies, of which around 24 carry most of the statistical weight, calibrated by 3 geometric anchors, tied to roughly 40 well-observed. Type 1. A supernovae in those hosts. That is the whole foundation. A few hundred stars doing the load-bearing work for a number that determines the age of everything. There is no way to increase that sample by much. It is limited not by telescope time, but by how many nearby galaxies happen to have hosted a well-observed supernova of the right kind, since photographic astronomy became reliable. You cannot commission more of them, which is why this particular test mattered so much. With a sample that small, a systematic bias would not average away. It would simply move the answer. The points fell on the line. The scatter tightened, as expected from the sharper images, which itself confirmed that the improvement in resolution was real and doing what it should. But the systematic offset that everyone had been looking for was not there. Averaged over the sample, the difference between the old measurements and the new ones was consistent with 0 at the level of 1% or 2%. The crowding corrections that the SHOES team had been applying for a decade had been essentially right. The distances did not shift. The expansion rate did not drop. The local number stayed at 73. Rias summarized the outcome publicly, and without ceremony, the essential content being that the new telescope had confirmed what the old one saw, and that the puzzle remained. He did not claim vindication in any larger sense. The correct thing had been checked, and it had held, which is a smaller and more useful statement than the one the moment invited. What had been eliminated was the leading explanation for how the local measurement could be quietly wrong, not disproved in some abstract sense, but tested with an instrument specifically capable of testing it, and found absent. At the same time, the same telescope was delivering data to Friedman's team. The Carnegie-Chicago program used the near-infrared camera to measure the red giant tip in overlapping host galaxies at Webb resolution. They also brought in a third method that had been developed in the interim, using carbon-rich asymptotic giant branch stars, old, cool, luminous stars whose brightness in the near-infrared clusters tightly enough to serve as another independent marker, and which live in the same uncrowded halos as the red giants. So Friedman's team was now running 3 separate stellar distance indicators through one telescope: red giant tips, carbon stars, and their own set of Cepheids. The results, published across 2024 and 2025, were internally interesting. The red giant tip gave a value close to 70. The carbon star method gave a value lower still, in the high 60s. Their own Cepheid measurement came out around 72, near but not identical to the SHOES number. Combined, the Carnegie-Chicago program reported an expansion rate close to 70, with an uncertainty around 1.5, and argued that their result was statistically consistent with the Planck value. The SHOES team disputed the analysis, particularly the treatment of the tip calibration and the selection of the galaxy sample. Friedman's team responded, "That exchange is ongoing, in the literature, in the way such exchanges should be conducted. The substance of it is narrow and technical and mostly comes down to 2 things. The first is sample overlap. The 2 teams do not use identical lists of host galaxies, and because the number of galaxies with both a well-measured distance and a well-observed Type 1, a supernova is small, a few dozen at most, adding or removing 2 or 3 objects moves the answer more than anyone would like. The SHOES sample is larger. The Carnegie-Chicago sample is smaller, but chosen for cleaner halos. Neither choice is wrong. They optimize for different things. The second is how much weight to place on each of the 3 stellar methods when combining them. Friedman's team averages the red giant tip, the carbon stars, and their Cepheids into a single number. Rias's team argues that the carbon star method is the least mature of the 3, having been developed most recently and calibrated on the fewest systems, and that averaging it in on equal terms drags the combined value down without justification. Both of those arguments are about statistics rather than physics, which is a sign of how far the observational side has been pushed. The instruments are no longer the limiting factor. The limiting factor is that there are not very many suitable galaxies in the nearby universe, and there is no way to make more of them. There is also a somewhat awkward fact, sitting in the middle of the Carnegie-Chicago results, that both teams acknowledge their three methods, applied to overlapping galaxies with the same telescope, do not agree with each other as well as they should. A spread of several units between the red giant tip, the carbon stars and their own Cepheids, is larger than the quoted uncertainties comfortably allow. Something in the stellar distance scale is not yet fully understood, and it is not the crowding. So the honest state of things after the most powerful telescope ever built turned its attention to the question, is this: the Cepheid ladder is not broken. The specific systematic that could most plausibly have broken it has been tested at high resolution and is not there. That is settled. The red giant and carbon star methods return values 2 to 4 units lower than the Cepheid ladder, with error bars that overlap Planck at the edges but do not sit on it. The disagreement between the two local teams is real. It is about statistical methodology and calibration rather than about instruments, and it has not been resolved. The megamasers and the lensed quasars, which use no stars at all, sit with the Cepheids in the low to mid-70s. And the microwave background, measured 3 separate ways, sits at 67 to 69. The telescope did not deliver a verdict. It delivered better evidence on every side, and the shape of the problem became clearer rather than smaller. There is a version of this that reads as failure, $1 billion of infrared observatory, pointed at a question it did not answer. That reading misunderstands what instruments are for. Webb was asked a specific, answerable question. Is the Hubble Space Telescope's Cepheid photometry biased by crowding? It answered that question definitively. The answer was no. Answering it definitively is what removed the comfortable explanation. As long as crowding was live, the tension could be filed as a technical problem, awaiting a technical fix, and a great many people filed it exactly that way. Once crowding was ruled out, the filing had to change. The quiet that followed those results was not disappointment. It was the particular stillness of a field that has finished checking its instruments and has to start checking its assumptions. There is a pattern to how a science behaves when this happens, and it is not the pattern that popular accounts suggest. Nobody announced that physics was broken. Nobody resigned. The immediate output was a large number of extremely careful papers, examining what the data now permitted and what it excluded, not proposing revolutions, but fencing off the territory in which a revolution could possibly live. That work is unglamorous, and it is the part that matters. Before you can say what new physics is needed, you have to establish precisely how much room there is for any new physics at all. And the room is small, because everything else in the model is already pinned down by other measurements. Doctoral students now build entire theses around testing one proposed solution. There are annual conferences devoted to this single number. Several thousand papers exist on it. The problem has become a subfield, with its own vocabulary and its own standard plots, and a generation of cosmologists has now been trained inside it, who did not experience the 20 years when everything fitted. For anyone who came into the field after 2015, a cosmology with a 5 sigma internal contradiction in it is simply what cosmology is. The problem stopped being about measurement and became about physics. Because if the microwave background is being read correctly, and the distance ladder is being read correctly, and the two still disagree, then what is wrong is not the reading. It is the thing that connects them, the model of how the universe got from one end of that gap to the other. That model has been right about almost everything for 25 years. Almost. The difficulty in fixing this is not that nobody has ideas. There are hundreds of published proposals. The difficulty is that the model being fixed is not fragile. Lambda cold dark matter is right about the acoustic peaks, the polarization, the abundances of hydrogen, helium, deuterium and lithium forged in the first 3 minutes, the large-scale clustering of galaxies, the ages of the oldest stars, the growth of structure from the seeds visible in the microwave background to the cosmic web we map today. 6 parameters, all of it. So a successful fix cannot simply raise one number or lower the other. It has to leave every one of those successes intact while changing exactly one thing. That is a considerably harder constraint than it sounds, and it is why, after 15 years and thousands of papers, nothing has been agreed on. There is a structural insight that organizes the whole landscape of attempts, and it is worth having before we go through them. The proposals divide into two families: those that change the early universe and those that change the late universe. The late universe fixes are the more intuitive ones. Perhaps dark energy is not a constant. Perhaps it's strengthened or weakened over the last few billion years in a way that would make the recent expansion faster than the standard model assumes, reconciling a low early value with a high measurement now. These are, in general, in serious trouble. And the reason is that we have independent constraints on the recent expansion history that are hard to bend. Baryon acoustic oscillations, the same sound horizon from the early plasma, imprinted as a preferred separation scale in the distribution of galaxies, and measured at many different epochs by surveys like the Sloan Digital Sky Survey. And now, with far greater precision by the Dark Energy Spectroscopic Instrument in Arizona, trace the expansion across the last 10 billion years. Type 1, a supernovae trace it too. Between them, they pin the shape of the recent expansion history quite tightly. Any modification large enough to close a 9% gap tends to break that shape somewhere else. There is a genuine live development here, and it deserves mention because it is the most interesting thing to happen in observational cosmology recently. The Dark Energy Spectroscopic Instrument, measuring baryon acoustic oscillations in millions of galaxies and quasars, has reported results that fit slightly better with a dark energy density that has been weakening over time rather than staying constant, at a significance that has climbed toward the 4 sigma range as the data has accumulated. If that holds, dark energy is not a cosmological constant. It would be a substantial change to the standard model. It does not, in its current form, resolve the Hubble tension. A weakening dark energy actually tends to push the inferred present-day expansion rate slightly the wrong way. But it is a reminder that the framework has at least one other seam under strain, and that the two strains might eventually turn out to have a common cause. There is a general result behind the failure of the late-time approaches, and it is one of the more useful things to have come out of the theoretical work on this problem. If you take the observed supernova and baryon acoustic oscillation data and ask, without assuming any particular model, what expansion histories are compatible with it, you find that the answer is quite tightly constrained over the last 10 billion years. Whatever dark energy has been doing, it has not been doing anything dramatic recently. The data does not permit a large late-time deviation, and the sound horizon, being fixed before recombination, cannot be changed by anything happening afterwards. So a late-time modification has to raise the present expansion rate while keeping the recent expansion history essentially unchanged and leaving the ruler alone, and there is very little room to do that. Several groups have shown that the space of late-time solutions consistent with all the data is close to empty. The conclusion most theorists have drawn is that if new physics is required, it is required early. Not because early-time solutions work well, but because late-time solutions demonstrably do not. The early universe fixes are where most of the effort has gone, and the reasoning behind that choice is worth following. Remember what the Planck measurement actually is: an angular scale on the sky, converted into a distance using a calculated physical size for the sound horizon. If the true sound horizon were smaller than the standard calculation says by around 7%, then the same angular measurement would imply a nearer surface of last scattering, and the inferred expansion rate today would rise into the 70s. 7%, that is the entire target. Shrink the ruler by 7% and the disagreement disappears. To shrink the sound horizon, you have to reduce the distance a pressure wave could travel before recombination. Since the speed of sound in that plasma is set by well-understood physics, that means reducing the available time, which means making the early universe expand faster than the standard model says, during the specific window when the horizon was being established. The leading proposal for how is called early dark energy. The suggestion is that for a brief period, a few tens of thousands of years, around the epoch when the sound horizon was being set, some additional energy component contributed to the expansion, then decayed away rapidly enough to leave no trace in the later universe. A field that switches on, does its work, and vanishes. The appeal is obvious. It touches exactly the quantity that needs touching, at exactly the moment it needs touching. and then removes itself before it can damage anything else. The problem is that it does not remove itself cleanly enough. Adding energy in the early universe changes more than the sound horizon. It alters the damping tail of the microwave power spectrum, the way the small-scale peaks fade, which Planck measures precisely. It shifts the polarization patterns, and most damagingly, it changes the growth of structure. A faster early expansion means matter has less time to gather under gravity, and to compensate while still fitting the microwave data, these models generally require more dark matter, which then overproduces clustering at later times. That runs into a second, quieter problem that has been sitting alongside the Hubble tension for a decade. Weak gravitational lensing surveys, mapping how the shapes of distant galaxies are subtly distorted by the mass between them and us, measure how clumpy the universe actually is today. Those surveys have tended to find the universe slightly less clumpy than the microwave background predicts. Early dark energy models push in the wrong direction on this, making the predicted clumpiness worse. The current position, after a great deal of effort by capable people including Vivian Pouline, Tristan Smith, Mark Kamiankowski and Karsten Jadamzik, among many others, is that early dark energy can relieve some of the tension, but cannot close it without straining something else. The versions that fit best still leave a meaningful gap. A related idea adds extra light particles rather than a new field. The standard model of particle physics gives 3 species of neutrino, and cosmology is sensitive to that count, because relativistic particles contribute to the radiation density and therefore to the early expansion rate. Add a 4th light species, a sterile neutrino, say, that does not feel the weak force, and the early universe expands faster, and the sound horizon shrinks. This runs directly into the first 3 minutes. The abundances of deuterium and helium produced by primordial nucleosynthesis depend exquisitely on the expansion rate at that time, because the competition is between nuclear reactions and the universe cooling out from under them. Deuterium, in particular, is a knife-edge measurement, observed in the absorption spectra of pristine gas clouds, backlit by distant quasars, the least chemically contaminated material we can find. The measured abundances match the standard model with 3 neutrino species to a few percent. Adding a 4th pushes the prediction out of agreement. Modified gravity takes the most radical route, that general relativity is not the correct description of gravity on cosmological scales. If the gravitational constant varied over cosmic time, or if gravity behaved differently in low-density environments, both the sound horizon and the growth of structure could shift. The obstacle is that general relativity is not lightly modified. It has been tested to extraordinary precision in the solar system, in the timing of binary pulsars, where the orbital decay from gravitational wave emission matches prediction to better than a part in 1,000, and now in the direct detection of gravitational waves from merging black holes. Any modification that operates on cosmic scales must switch itself off completely on small ones. Mechanisms for this exist, and they are called screening, and constructing one that also reproduces the microwave background and the observed clustering has proved formidably difficult. The people working on it are serious physicists, not cranks, and they are entirely aware that they have not succeeded yet. Then there is the simplest idea of all, that our neighborhood is not typical. If the Milky Way sits inside a large underdense region of void, then the local expansion rate would genuinely be higher than the global average, because there is less matter nearby to slow things down. Local measurements would read high, while the microwave background, averaging over the whole observable universe, read the true value. Both would be correct. Nothing new would be required. It is testable, and it has largely been tested. There is a real underdensity in our vicinity. Galaxy surveys show that we sit in a region somewhat emptier than average, extending a few 100 million light-years. But its depth is modest. Detailed modeling of the galaxy distribution and the velocity field of nearby galaxies indicates that a void like ours could account for perhaps 1 or 2% of the discrepancy. To account for 9%, it would have to be so large and so empty that it would contradict the galaxy counts we can directly perform. Beyond these, a long tail of proposals. Dark matter that decays into radiation early on. Interactions between dark matter and dark energy. primordial magnetic fields adding pressure to the plasma and altering recombination, a small spatial curvature, a recombination process that proceeded slightly differently than modeled. Each has advocates. Each has papers, conference sessions, doctoral students. None has convinced the field. The scoreboard, stated plainly, is that we have a 5 sigma discovery and no accepted explanation for it. That is an unusual condition for a mature science to be in, and it is not a comfortable one. So here is the honest inventory. We do not know the present expansion rate of the universe to better than about 9%, despite 2 independent measurements, each claiming a precision near 1%. We do not know the age of the universe to within 1 billion years. We do not know whether the model that has organized cosmology for 25 years is missing a component in its first 400,000 years, or whether one of the most scrutinized measurement chains in the history of astronomy contains a systematic that has outlasted every attempt to find it. We do not know why 2 local methods, both using stars, both measured with the same telescope, still differ by more than their error bars allow. Those are not rhetorical unknowns. They are the actual working state of the field in the middle of 2026. What comes next is largely a matter of waiting for instruments. The Dark Energy Spectroscopic Instrument continues to accumulate galaxy spectra by the millions, sharpening the recent expansion history. The Euclid telescope, launched by the European Space Agency in July 2023 and also operating from the second Lagrange point, is surveying a third of the sky to map the distribution of dark matter through weak lensing. The Nancy Grace Roman Space Telescope, with a field of view roughly 200 times that of Hubble at comparable resolution, is designed among other things to find Type 1a supernovae in enormous numbers and to measure Cepheid distances with far better statistics. And the gravitational wave detectors keep improving. Each observing run brings more events, better sensitivity, better sky localization. Standard sirens with identified host galaxies remain rare, but they are not going to stay rare. When there are 50 of them, the expansion rate will have been measured by a method that owes nothing to any of the arguments in this story. That is the most likely resolution, and it is worth being clear about what kind of resolution it would be. It would not be an argument 1. It would be a third party arriving with an answer that neither existing camp had any stake in. There is also a real possibility that the answer, when it comes, is not clean, that the local number is right and the microwave number is right, and the reconciliation involves a component of the early universe that we have not yet imagined and will not find satisfying when we do. And there is a possibility that deserves to be stated last, because it is the one that gets least attention and is not obviously the least likely. The tension might resolve mundanely. It is entirely possible that in 5 or 10 years, someone will identify a systematic in the supernova standardization, some dependence on host galaxy properties that shifts the calibrating sample relative to the distant one by a few percent, and the local number will drift down to 69, and the red giant measurements will be understood to have been pointing at it all along, and the whole thing will be filed as a hard-won lesson about the difficulty of measuring astronomical distances. That outcome would not be a disappointment. It would be the ordinary way science works, and it is roughly what happened to the previous fight about this same number. It is also, notably, the outcome that several of the people closest to the data consider most probable. Friedman has said as much. Rios has never ruled it out. His position is that nobody has found it, not that it cannot exist. Anyone reading this story as a certain sign of new physics is reading ahead of the evidence. What the evidence supports is narrower and, in its way, more interesting. That we have looked very hard for the mundane explanation with the best instruments we have ever built and have not yet found it. 2 clocks then, in a dark room. One of them is ticking in the walls around you tonight, not metaphorically. The photons released when the universe cleared 13.8 billion years ago are passing through this room, through the ceiling, through you, at a rate of hundreds per cubic centimeter, and have been doing so without interruption since before there was a single star. In their pattern of hot and cold spots is a ruler, laid down when the plasma froze, and that ruler gives 67.4. The other clock is made of stars, and it starts in a room in Massachusetts in 1908. where a woman, comparing photographic plates, noticed that the brighter variable stars took longer to pulse. It runs through the water molecules orbiting a black hole in Canes Venatici, through the parallaxes of 1 billion stars measured by a satellite at the second Lagrange point, through the deaths of white dwarfs at a threshold mass calculated by a teenager on a boat from Madras, through the Webb telescope, which looked at Leavitt's stars with the sharpest infrared eyes ever built and found nothing wrong with them. That clock gives 73. The gap between them is 1 billion years of history that we cannot currently account for. Everything we have built to close it has instead confirmed both sides. The telescopes worked. The teams checked each other. The independent methods came in and stood with the ones they were meant to check. Every single thing that could have gone right went right, and the disagreement is still there, unmoved, sitting in the literature with error bars that no longer touch. We measured the universe with great care, and it returned 2 answers. At some point, presumably, a third measurement, or a better theory, will tell us which of them we misread, or what we failed to include. Until then, this is simply where the boundary of the subject is not somewhere far away and unreachable, but here, in the middle of the best measured quantity we have. The room is dark. Both clocks are still running,